Physically traveled, and if I would have met you people face to face, it would have been wonderful. Nevertheless, whatever opportunities we are having, let's make use of those. So I will share my screen, and then I will start my presentation.
Sure.
So I have closed my. I hope you can see my screen and the presentation.
Yes, visible, sir. Yes.
Okay. So as Mr. Jha explained, actually we had planned two talks. One regarding calculation of earthquake forces, and another one regarding the ductile detailing, because these are the two major aspects of earthquake resistant design. And then whatever questions are there, whatever queries you are having, please let us know. We will try to answer all those in these 2 days. So this first talk which we are having today, I will talk about calculation of earthquake forces. And as all of you are aware, the Nepal building code has been recently revised, and it is now a quite good code. Let me say that it is better than Indian code in some aspects now, and I congratulate you and those who have been behind this this revision of the code. And some of them are good friends, Professor Maski and Professor Rajesh Dhakal, and I can see there is good contribution from all those. And I recommend to the designers in Nepal that they should have good understanding of this code. This code is really good, so they should understand this code and use it in their designs, so that the infrastructure there in Nepal is earthquake resistant. It is safe to the extent possible, because whole of the Himalayan region, including Nepal, is quite seismic. And due to that seismicity of Himalayan region, our structures are subjected to extreme ground shaking at different times. And recently, in 2015, we have seen in Nepal that there was a major earthquake, and it has caused large-scale devastation. We have learned several lessons from there, and this is the right time that the code has been revised and people start practicing it. So when I say earthquake, many things come to your mind, but what I mean to start with is this plot of the ground acceleration. Similar plots we get after every earthquake using an accelegraph. So accelegraph is nothing but an accelerometer which records acceleration of the ground. And earthquake causes this sudden acceleration of the ground, plot of which with time is shown here. Now, this plot of earthquake is its unique signatures. So every earthquake has its unique signature like this, and it has some peculiar characteristics. One characteristic is that earthquake causes an acceleration in all the directions, both horizontal and vertical direction, but the horizontal component is more predominant and it is more damaging. Our structures are subjected to more damage because of that horizontal component of the earthquake. So the first thing we learned about earthquakes was that earthquake causes a horizontal force on our structure. And this is an inertial force, a fictitious force, something similar to the feeling when we are standing in a bus and the bus starts suddenly moving or it stops suddenly. Then we feel like somebody has pushed us backward or pushed us forward in case of braking. But actually nobody has done that. Same thing happens in case of earthquake. Actually the ground moves, and because of the inertia property of the structure experiences a fictitious force, and that force is much larger than the capacity of the structure, because the shaking in case of a major earthquake may be very vigorous, and at the same time in horizontal direction our structures are weaker. So inherently any structure, any object if you take, is weaker in transverse direction. Suppose I give you this pen and I ask you to break it. You will not try to break it like this. You will try to break it always like this. So if a stick is given to you, your brain knows from your daily life experience without any calculation that it is much weaker in bending. In the transverse direction, it can be broken much easily. And in the axial direction, it will resist large force. Same thing happens with our structures, with buildings. In vertical direction, those are always subjected to 1g acceleration due to gravity. 1g is always acting. In the horizontal direction, it is only a fraction of g. So if we talk about, let us say NBC105 2020, then this horizontal earthquake or acceleration due to earthquake is varying between 0.25 g to 0.4 g. So it is only a fraction, 40% of that force, which is acting in the vertical direction. But still, our buildings are difficult to be designed for this small fraction of g. Whereas in vertical direction, all those buildings are resisting 1g very easily. And the reason for that is that our structures are inherently weaker in horizontal direction. All objects, all natural and man-made things which we have on Earth, those are weaker in the transverse direction and stronger in the vertical direction. So this was the first learning about earthquake. And based on that, our initial codes. So in India, I'm not that much aware of the history of earthquake code in Nepal, but I will take some examples from India. So India first code came in 1962, and the understanding of earthquake resistant design started early 1950. So 1949, 1950, at that time, this started. And the first code when we had, that was based on seismic coefficient method. And in seismic coefficient method, we just prescribe that a fraction of the weight will be acting in the horizontal direction, and we design our structure for that fraction of weight in the horizontal direction. So that was the first method of analyzing and designing structures for earthquake. The other peculiar characteristic of this signature of earthquake, which I had shown you, you can see that the acceleration is changing its direction rapidly. So it is a reversible type of force it is applying on our structure. That force is changing its direction very rapidly within a fraction of a second, and this total duration is roughly 30 seconds. So within 30 seconds, you can see how many times it has changed the direction. If we compare it with the other forces which we are designing our structures are dead load, live load, and wind load. Dead load, live load are in vertical direction, and as I said, that inherently in general, all our structures are quite strong in the vertical direction, so there is no issue. Easily we can design for dead load and live load. Wind load is in horizontal direction. That is the similarity with the earthquake. And another similarity with earthquake is, if you see in this plot, this is the plot of velocity with time. So here also you can see that there is fluctuation in the wind velocity. So wind velocity is also changing with time. But the difference you see here, the wind velocity remains in one direction. It is fluctuating, but it is not changing the direction. So there is a mean wind velocity and it is fluctuating around that mean wind velocity. On the other hand, in case of earthquake, if you see, the earthquake acceleration is fluctuating, is changing around the zero line. Okay, so it is changing its direction. So it is a reverse cyclic type of force it is applying on the structure. And we take advantage of this reverse cyclic loading, which I am going to discuss soon in today's talk. We take advantage of this reverse cyclic nature. This is very important for us for designing the structures. And by virtue of this, we are able to design our structures for much lower force than which will be actually acting because of the inertia action on our structure. And still, our structure can survive the earthquake without collapse. It will damage, but it will survive the earthquake without collapse. Why? Because the earthquake, which is much more than the capacity of the structure which we have provided in our structure, the applied force is much larger than that. So that applied force will cause yielding in our structure. It will cause some damage in our structure. The structure will go on deforming, but still till the structure was deforming, within that time, the earthquake reverses its direction and it saves the structure from collapsing. So because of this reversible nature, we are able to save the structure, same earthquake which is causing damage to the earthquake, the damage to the structure, save the structure by coming in the opposite direction. So this reversible nature of earthquake is very important, which we do not find in any other type of load. That's why the design philosophy for earthquake is very different than the design philosophy for wind, dead load, and live load. In all these three loads, there is a factor of safety. The capacity of the structure is more than the demand. So whatever demand is coming from dead load and live load in vertical direction, actual capacity of a structure is larger than that. But not in case of earthquake. In case of earthquake, the capacity of the structure which we are providing, following the code also, when we do the proper design, even then the capacity of the structure is much lower than the demand which will be coming on the structure. And it is about 10 to 20% of the actual demand which will be coming on the structure if the structure was to be designed for the full earthquake force. So we design for only 10 to 20%, and rest of it is taken care of by this reversible nature of earthquake loading. So this reversible nature of earthquake loading is very important. We take advantage of this, but that advantage comes at a cost. And what is the cost? The cost is that we need a more detailed analysis of our structure. The structure undergoes nonlinear, inelastic, and cyclic response because we are applying a cyclic load. So it is a dynamic phenomena. It is nonlinear because the earthquake force is much more than the capacity. So our structure yields. So the analysis becomes complex. The life of the structural designer becomes more complex when dealing with earthquake load as compared to dead load, live load, and wind load. And to help you in that, we are having these codes, and I will tell you how the code helps in this. The first question which we have to answer is that which earthquake I should design for. So if you take some of the past well-known earthquakes which have caused large scale damage, so you can see their signatures are very different. Any two structures or any two earthquakes, sorry, will never have same signatures, same accelerogram. So accelegrams are going to be different, and as a result, it becomes difficult that which accelerogram or which earthquake record which has been recorded in the past I should use, because the earthquake which is going to come at my site, which will affect my structure, will be different than all those earthquakes which we have recorded in the past. So it is a really tough question, which one I should take. To answer this, we try to understand the different characteristics of ground motions. So that those characteristics which govern the damage potential of a ground motion, there are three characteristics. One is amplitude of ground motion. So amplitude of ground motion is the peak ground acceleration or peak ground velocity or peak ground displacement. In short, we call PGA, PGB, and PGD. So that is the amplitude. So larger the amplitude here, more damaging the earthquake will be. Then the second important characteristic is frequency content. So the response of the structure, the actual force which will be acting on the structure will maybe less than mass into ground acceleration. It may be more than mass into acceleration, depending on the tuning between the ground motion and the structure. So every earthquake record here can be considered as consisting of a large number of harmonics or having a band of frequencies. So it is having a band of frequencies, and out of that band of frequency, there is a predominant frequency range where the contribution or where the maximum energy is there, which is having, if I do a Fourier transform of this or I plot a Fourier spectrum, where I will get peaks of the Fourier spectrum. So those are the frequencies where most of the energy is concentrated. And if the frequency of my structure is within that range, predominant frequency range of the earthquake, it will be subjected to larger forces, which may be more than the ground acceleration. And In case my structure is having a frequency away from the predominant frequency of the earthquake, frequency and period are related. We know period is inverse of the frequency. So the period of the structure is such that it does not have tuning with the earthquake. Its frequency is quite different than the predominant frequency range of the earthquake. Then the response will be less. The force which will be applied on the structure will be less. Fortunately and unfortunately, our low-rise buildings have their tuning with the structure. So if we are having building, let us say up to 7 to 10 stories. So generally the frequency of those 7 to 10 stories buildings is in that range in which the earthquake is also having its predominant frequency. But if we are fortunately in case of taller buildings, let us say I'm designing a 60-story building or 80-story building, then the frequency of vibration of that building is much shorter, much smaller, or the period is much longer than the predominant frequency of the earthquake. And fortunately, the force acting on a tall building will be lesser than mass into ground acceleration. So this effect we have to take into account while designing our buildings. Then duration of earthquake is also important because the damage which is caused to the structure by earthquake is cumulative. So you can see that earthquake is having, any ground motion is having several pulses of acceleration, and each pulse will cause some damage to my structure, and every time the damage will be accumulated. You are aware of the phenomena of fatigue. So what happens in fatigue, that if a bridge is subjected to a vehicle load due to rail or due to our road vehicles, so every time the vehicle is passing, it is subjected to some stresses. Those stresses are much less than the yield stress of the bridge, because we do not want our bridge to yield under dead load and live load. So it is much lower than its capacity. Still, if millions of vehicles pass over the bridge, it is subjected to millions of cycles, then it fails due to fatigue. Although the stresses were never more than the yield stress, much less than the yield stress. The stresses were within the capacity, because every time a vehicle is passing, it is causing a tiny damage to my bridge, and that tiny damage goes on accumulating, and if it gets accumulated millions of times, then it will cause failure of my structure. In case of earthquake, what happens? The earthquake force is much larger and it causes yielding of the structure. The stress is exceeding the yield stress. After yield stress, the stress is not exceeding, the strain increases. So the strain is more than the yield strain, so damage is much more. And it is something like this: if I give you a steel strip and ask you to break it, what you will do? You will bend it. You will bend it permanently, okay, in one direction. What does that mean? That means that the strip has yielded. So yielding, post yielding means that there is a permanent deformation. So you make a permanent deformation in your strip and then bend it in the opposite direction permanently. So if you are bending the strip 3-4 times such that you are giving it permanent or plastic deformation, then it will fail in few cycles. It will not require millions of cycles. In few cycles, it will fail. This phenomena is called low cycle fatigue. And that's what happens during earthquake. So during earthquake, when earthquake is acting in one direction, let us say the reinforcement is subjected to tension. Then when the earthquake reverses its direction, the reinforcement may be subjected to compression. And these cycles of tension and compression, every time when the reinforcement yields in tension, its length increases a little bit. And when it is subjected to compression, it tries to shorten, but reinforcement cannot shorten, it buckles. So it is buckling and then straightening, it is buckling and then straightening. And in that process, the fracture of the reinforcement occurs. So that's why the duration of earthquake is also important. And in our modern analysis, which we are doing using nonlinear time history analysis, so there we are taking into account the duration of earthquake also. But in our conventional analysis, we take into account the first two characteristics of the ground motion: amplitude of ground motion and frequency content. Both these properties together can be represented by response spectrum. So I do not know whether you are familiar with the concept of response spectrum or not, but for the benefit of your understanding, I will tell something about that. So if you have a single degree freedom system, you are aware with the concept of the single degree freedom system. It is a simple structure which is consisting of one mass connected by one column. So all the mass is here, column is weightless, and here all the mass is there, and column is providing the stiffness and damping. This can also be represented by a spring, mass, and desk point. That is the analytical representation of the same thing. Physically, it is representing a single degree freedom system, means the single story building. So a single story building or a water tank or a column pier can be thought to be similar to the single degree freedom system. And when the single degree freedom system is subjected to the earthquake ground motion, we will get a response here. So acceleration of this mass will be different than the acceleration of the ground. That will depend on the stiffness and mass, or in other words, the period of vibration of this single degree freedom system. So the period of vibration or frequency and damping of this single degree freedom system will decide what response we are going to get. So if I have a number of such single degree freedom systems with increasing height and mass, and when the height and mass is increasing, the period is increasing. So if I have a number of single degree freedom system with increasing period, and I apply the same ground motion here, the same earthquake ground motion here, then what will happen? The response of these single degree freedom system will be different because their periods of vibration are different. So their response will be different. If I take the peak response of each of these single degree freedom system and plot along with the period or frequency, period is just inverse of the frequency. So I can plot this either in terms of frequency or in terms of period. And I take the peak response. Peak response, I mean either peak acceleration of mass, not of the base. The peak acceleration of the mass. Peak acceleration of the base, the ground, that is called PGA, peak ground acceleration. What we are getting from the mass, that is the response. So if I take the peak acceleration of that, I will get an acceleration response spectrum. If I take displacement, I will get a displacement response spectrum. If I take velocity, I will get a velocity. Peak velocity, if I plot, I will get a velocity response spectrum. The most commonly used response spectrum is acceleration response spectrum. And actually, we use a pseudo acceleration, not the real acceleration, but that is very similar. I don't want to go to that aspect of the theory of vibration. Those who are interested may learn it separately, but it is very similar to acceleration. So it is like the acceleration of this mass, and if I multiply that acceleration with the mass of this single degree freedom system, I will get the force acting on that. So that's the advantage of this concept of response spectrum, that I can read the force acting on my structure directly, or rather the force per unit mass I can read from here. It is spectral acceleration. Spectral acceleration means that it is ratio of force which is occurring in this column to the mass. So force divided by mass, or force per unit mass, that is this spectral acceleration that I can read from this response spectrum. If I do it for one earthquake, I will get something like this, a plot like this. And corresponding to zero period here, zero period means my structure is having frequency equal to 1 upon 0, infinite frequency. So which type of structure it is representing? It is representing a very rigid structure, which is not vibrating at all. It is moving along with the ground. So it is like a huge block of concrete embedded into the ground. So it is moving along with the concrete, along with the ground. And that's why its acceleration will be same as that of the ground. So the peak value at zero period will be the peak value of this rigid block, which is nothing but very close to the PGA, peak ground acceleration, and it is called EPGA. Sometimes people write it just PGA, but it is not exactly equal to PGA. It is close to PGA, but we call it more precisely effective peak ground acceleration, or EPGA. This is very important. This EPGA is used in all our codes, Indian code as well as Nepalese code. This EPGA is used. So this EPGA is that if I have a very rigid structure, a concrete block, and that is subjected to earthquake shaking, then whatever will be the peak acceleration of that block, which will be very close to the PGA, that we call EPGA. Same is also called ZPA, zero period acceleration, because this is representing the acceleration of the single degree freedom system, which is having zero period. So this is also called ZPA and represented by Z. And the same is also used in zone factor. So zone factor Z is ZPA, zero period acceleration, and that is equal to EPGA, and it is nothing but the ordinate of this response spectrum at zero period. So if I plot such response spectra for a number of earthquakes with the same EPGA, okay, so EPGA is same, and I have plotted number of earthquakes response spectra, you can see that all these are zigzag. If I take average of those, then you will get this dotted shape. So something like this we are getting. But we idealize this. Actual response spectrum is not like this, but we idealize it as it has been given in the code. You might have seen that there is an increasing arm, then there is a constant acceleration or plateau region, and then it is decreasing. Okay. In Indian code, it is decreasing proportional to 1 upon t. In Nepalese code, it is decreasing proportional to 1 upon t to the power 4. Okay. We will see that, compare that, what are the implications. So this range where it is flat, this is called acceleration control range. And this is controlling the response of short period structures. You can see in this graph, it is something like 0.6 or 0.7. So this is acceleration control range, or what we call short period range of our response spectrum. And beyond this, it is called long period range. And this is also called velocity control range. So up to 4 seconds, this is velocity control range. If we go beyond that, then there is another range which reduces even more rapidly, which we call displacement control range, where the response is controlled by the displacement of the ground. So 3 ranges in response spectrum. We have a flat region, a decreasing acceleration region, and then we have another region where it is reducing even more sharply, which we call velocity control range. So acceleration control range, velocity control range, and displacement control range. Displacement control range is governing the response of very tall buildings. So if I have 40-story plus, which will have the period roughly 0.1 into 40, so 4 seconds. So beyond 4 seconds or 6 seconds, in that range, the displacement control response spectrum governs. Okay. So far, Indian code as well as the Nepalese code, it is not giving the displacement control range. Okay. In the future code, in the revised code, Indian code, most probably we will have a displacement control range also. But when we look at the Euro code or American code, there we have these 3 ranges distinctly given. So acceleration control range, velocity control range, and displacement control range is distinctly given in those codes. So what I wanted to show here is that individual earthquakes may be zigzag, but when we take their average, we get a relatively smooth curve, and that smooth curve also we idealize by this regular shape curve, and our codes give that curve, and actually these codes gives the shape of that response spectrum. How that shape is obtained? That shape is obtained by normalizing the response spectrum. So that response spectrum, spectral acceleration at any period ti is divided by 0 period spectral acceleration, that is EPGA. So we divide it by EPGA, then we get the normalized response spectrum or spectral shape. And what is given in our codes is that shape. So that CHT, which is available in NBC105, you might have seen. So this is giving the shape. What you see here, this is for equivalent static method, and in equivalent static method, that increasing arm part is missing. So this part is missing. I will tell you later that why that has been removed from here. More realistic is this one, which is for modal analysis or for mode superposition analysis. Here you see that this increasing acceleration part is also there. Then there is a flat part, and then there is a reducing part. And NBC gives up to 6 seconds. And for different types of soils, different shapes are obtained. And you can see these shapes are changing drastically. Here, in case of soil type A, which is a stiff soil. So if you take a very stiff soil, okay, I will go to the definition.
Hello, sir.
Yes.
Sir, it's Tajul.
Yes, Tajul.
Sorry, sir, for interruption. Actually, I just wanted to let you know you are still set with the IS structure background. So is it you have done or it was there?
My screen is
That IS structure retrofitting course background is still set.
my screen is stuck.
No, sir.
No,
That's just your background image, sir. Like your photo is there, and in the background there is some other.
So that
system
IS
advertisement.
structure retrofitting course background
Okay.
is set.
Last time when I was doing a presentation in IS structure, they put it somehow. So I have to
No problem. No problem, sir. Yeah, no problem.
let me remove it. I mean,
Yeah.
that's not good. Where is the meeting control? I have to.
It is there, sir. In the mute stop video, something is there. In the stop video, there is an arrow where if you click, there will be video settings.
I think I have to stop share, then only it will come. Yeah. I will stop sharing. Sorry, where?
In the mute, and there is stop video in the bottom left. So in the stop video, there is an arrow where if you click, there will be video setting. Yeah. So there will be video setting. So did you go to video setting?
Left background, you will see start video options.
Start
Yes.
video. I am not getting that. Speaker.
Left bottom side, sir.
Yeah, left, bottom left. I'm having mute. No.
And then
yeah,
stop video after that.
beside
After that,
that,
stop
start
video.
After that, stop video. Okay. So,
So
stop
there is a
video. I have
choose.
to go.
So
And
choose
click on
virtual
that arrow,
background.
sir.
But
Yes.
choose virtual background.
Yeah,
Okay.
yeah.
So I will say none.
None.
So somehow my system has remembered that, and that's it.
Yeah,
I
that
think
is good.
it has gone.
It's gone. Yeah. Now we can see your office now.
Okay.
I'm sorry, sir. Actually, I was seeing it from long back, but I thought you have said that's why I was
I
worried.
was not able to see, so that's why,
Yeah.
because I was not seeing my video. So anyway,
Okay. So no.
so thank you, thank you, Tajul. All right, so let's continue with our discussion. So we were talking about this concept of response spectrum and spectral shape. So these spectral shapes are idealized spectral shapes. These are sort of envelopes, so that for most of the recorded earthquakes, the response spectrum lies below this or close to this. There should not be large difference. And the shape depends upon the soil class type. So you can see that width of this flat region, that depends on the soil type. And if you compare it, I will show later on a comparison with the Indian code. So this is much wider than the Indian code. And I will tell you the region also. In the beginning, I said that there are some aspects in this code which are better than Indian code, more advanced than Indian code. This is one of those. So you can see here, the shape of the response spectra are very different depending on the soil type. So you can see that soil type can change the earthquake forces acting on a structure drastically. So far, we have not been giving so much importance to the soil type or the site class. So depending on what type of soil or site we have, the earthquake force can increase many times. For example, if your building is, let us say, 20-story, 2-second period. So at 2-second period, you see how much is the difference. So if your structure is on rock, then it is something like 0.3. On the other hand, if it is on soil type D, then you can see it is 2.2. So from 0.3 to 2.2, 7 times increase in the forces. And if somebody has made a mistake in designing a 20-story building, in determining its site class, then you can easily imagine what will happen. You are designing for 1/7 of the forces which you should design for. So it's difficult to withstand that earthquake by the structure. So this range especially is very important, from 0.7 second to roughly 2.5 seconds. This range, and you will see most of our structures which you will be designing come in this range. So 0.7 second means 7-story building, and 2.5 second means 25-story building. Currently, this must be the height. If I can imagine, I have not been to Kathmandu for a long time, but I can imagine that this must be the range of the buildings which are coming up currently, which you people may be dealing with. So please be very careful about this soil type, site class. And I have seen, I was very happy to look at that an optimum combination of sophistication and simplicity has been involved in the Nepalese code. So the effect has also been included, and at the same time the classification has been kept simple, so that based on the SPT value itself, because this site classification is actually based on shear wave velocity, but you need sophisticated instrument and measurement for shear wave velocity. So if somebody is constructing a building in US or UK, then they will be going by BS30, shear wave velocity in the top 30 meters. But in our countries, we do not have that type of instruments available everywhere. So we will go by simple test of SPT. And whatever N values we are getting, based on that also, and based on our understanding of the soil type, we can do the site classification, and that has been attempted nicely in this NBC105 2020. Now, why this such large period? Is it possible to have such a flat range? Earlier, if you compare with the Indian code, even the current Indian code, it varies from 0.4 to 0.7. So even for soil type 3, it is 0.7. And here we are talking about 2 seconds, flat region up to 2 seconds. Why? Is it reasonable? The answer lies in the recent earthquake recording in Kathmandu. So in Kathmandu Valley, this was the record. So what you see, this curve, which is light black color, is smooth curve. This was during Kobe earthquake, recording was done. And what we have recorded in Kathmandu, you can see where the peak is occurring. Peak is occurring at 4.5 seconds, between 4 and 5 seconds, the peak is occurring. Even much beyond than 2 seconds, which has been done here. So we can have peak even here at such a long period. And if I was following this Kobe earthquake response spectrum, then my ordinate here would have been, it would have been very low. So it is hardly anything. I mean, it is several times, 5 or 6 times of what I will get from Kobe earthquake. So this has happened because of this deep soft soil deposit in Kathmandu Valley. And that has caused amplification at long period. And for such situation, we have to take care like this. Earlier, it was thought that this soft soil deposit is problem of plain areas, flat areas, foothills, Tarai region. But we are seeing even in valleys deep within the hills, within the Himalaya, those valleys, wherever we are having, like Kathmandu Valley, there this problem is very severe. So it is applicable, this soil amplification is applicable to hilly regions as well. And this Gurkha earthquake has taught us this lesson. Okay, so the same shape is described in terms of these equations and these coefficients. These are self-explanatory. You have to just put, depending on which type of soil you have to read the value of Ta, Tc, alpha, and K, and that you have to put in these formula, and you will be able to plot the response spectrum. Okay, now let us compare these provisions with the Indian code. So let us see what happens in case of soil type A. Soil type A is actually the rock. In both the codes, this is very stiff soil. So it is similar in both the codes. So if my structure is located on rock, then soil class A will be applicable. And we can see here that this maximum amplification is 2.5 times. In the shape, the maximum value is 2.5. Okay, and it the flat region continues from 0.1 second to 0.5 second. In Indian code, it continues on rock from 0.1 second to 0.4 second, not 0.5 second to 0.4 second. So here it has been slightly flattened. Okay, and this part, which is from 0 to 0.1 second, this is same. It comes out to be the same. If you substitute the value of alpha 2.5 here, you can see it comes out to be same 1 plus 15t, which is there in Indian code. So this part is similar, but here we have a significant change. In Indian code, in velocity control range, it is given 1 by t. Okay, whereas here you see this equation. This equation means that it comes out to be some constant divided by t square minus some constant divided by t4. So it is reducing with the power of t to the power 4 or t to the power 2. Okay, so this is much more rapid reduction. So there is a very steep reduction in Nepalese code as compared to Indian code. In Indian code, the decrease is relatively mild. So it is proportional to 1 upon t, whereas here it is proportional to 1 upon t to the power 4. So that difference is there. So this is a difference from IS1893. Now, different types of soil classifications. You can see in the code, depending on the N value and the type of the soil, we can define a site class. A table is also given in the code where you can define what this soft soil and firm soil and stiff soil is mean based on the depth and the undrained shear strength, as well as in case of cohesionless soil based on N value. So here we will use N value, here we will use undrained shear strength. And accordingly, you can define which type of soil it is, and you can assign a site class to it. Now here I have shown the comparison of the response spectrum, design response spectrum from Nepalese code and the Indian code for a Z value of 0.3. So if you see EPGA is 0.3 for both, I have taken EPGA at 0.3. And what you see with this red color, this is NBC, and what you see with the blue color, this is IS code. And you can see that in the short period range, it is NBC which is giving higher value, and in long period range, the IS code is giving higher value. Okay, so I told you that the decrease in NBC is much steeper. So here you can see there is much steeper decrease in the value of spectral acceleration, whereas it is relatively mild in case of Indian code, and from 4 second to 6 second, it has been taken constant. Currently in Indian code 2016, you might have noticed that this is flat, but here it continues with the same curve proportionate to t to the power 4. Okay, this is for soft soil. So if I take type C from NBC and soft soil from Indian code and I compare, we can see that the difference is even more. And the two differences which I pointed out to you, that the flat region has increased and the decrease is much steeper. So you can see here with for long period structures, the reduction in spectral acceleration is much steeper in case of Nepalese code. And if I take the very soft soil in NBC, the difference is much more drastic. So you can see Indian code, we have the type 3 soil, which is the most soft soil. In both comparison, in the previous comparison as well as this comparison, we have used type 3 Indian soil. So type 3 curve from Indian code, and this is soil type D in the NBC. and we can see how much difference is there in the two codes, especially close to this 2-second period. So between 1 second to 3 seconds, there is large difference, and most of our buildings will be here. So I'm sure that after this code, the design of buildings in Kathmandu area, where you have the deep soft soil type D, is going to change drastically. The forces in Kathmandu area for design of buildings are going to change a lot after this code, and those are for good. If you are using, on the other hand, this Indian code, then your design will be non-conservative. Okay. Now we have to, in our quest to define the earthquake label, which we should use in our design, we have to define the label of earthquake. So the label of earthquake, which we call hazard label, we define in terms of either a return period or a probability of accidents. So commonly used probability of accidents are these: 50% in 50 years, 20% in 50 years, 10% in 50 years, 5% in 50 years, and 2% in 50 years. Why 50 years? Because we consider the normal design life of our buildings as 50 years. In case of bridges, it may be more, 100 years or 75 years. But in buildings, usually we consider 50 years as the design life. So the probability of accidents in the life span of the structure, our buildings. So 2% in 50 years, this is the maximum lifespan we have, or maximum probability within the lifespan of the structure we have considered, which we call maximum considered earthquake MCE, and its return period is 2,500 years. So this is the third characteristic of earthquake, that it is a rare phenomena. The average return period of the maximum earthquake, which we are considering for safety of our structures, is 2,500 years. It is a very rare phenomena. In 2,500 years, 50 generations, if I assume 50 years as the design life of each structure, so we can see that the 50 generations of these structures will pass by in 2,500 years. So rather than designing those 50 generations of structures to large earthquake force, what we do, we design the structures for lower earthquake force and be prepared for damage. So we want, or we design our structures to get damaged during earthquake. We have invited that damage because we are not designing our structures to remain intact under this MCE, large earthquake. So the structure will get damaged, and it is quite possible that the structure may not be usable after, it may not be even repairable after the earthquake. We have to remove it and construct again. And even in that case, what we are doing, in place of 50 structures, we will be constructing 51 structures in 2,500 years, because one structure will be sacrificed. Still, cost of constructing 51 structures will be lesser than constructing 50 structures strong enough not to get damaged during earthquake. So that's why we have taken this decision that we want to design our structures to not collapse during MCE, maximum considered earthquake. So that's what we are expecting from our structures, that these structures may get damaged, but these should not collapse, because collapse of the structure will cause large loss of life. The other important earthquake which we use is this one, 475 years return period, design basis earthquake. So design basis earthquake is most commonly used for design, and it has a probability of accidents 10% in 50 years. Currently, the zone factor Z, which is given in Nepalese code NBC105, is corresponding to DBE, 475 years return period, or 10% probability in 50 years. On the other hand, in Indian code, the zone factor is somewhere in between 475 and 2475. Actually, that zone factor, when we multiply by 1.5, then it corresponds to MCE. So if I have to compare the zone factor of Indian code and Nepalese code, I have to keep in mind that the zone factor given in Indian code is MCE divided by 1.5, and that given in Nepalese code is for DBE, and we should consider their parity. then only we can compare. I will show a comparison to you. So in Nepalese code, the contours are given for this zone factor, and this zone factor is varying from 0.25 to 0.4. You can see here it is varying, and then it starts reducing again for Indian side also. So unfortunately, to the Nepalese people, through the Nepal, the highest intensity contour is going. If you go away towards Chinese side or you move towards Indian side, then the PGA is decreasing, EPGA. This zone factor is nothing but, as I said, effective peak ground acceleration, zero period acceleration. So that is decreasing. Okay, the peak occurs somewhere here along this line, which is passing through Nepal. Okay, so this is the maximum. So depending on the location of my site, I can choose what value of Z I am getting from this map. And then I have to calculate the earthquake forces, and we use some load combinations for design. And the load combination given in NBC105 is dead load plus lambda times live load plus earthquake. So dead load is taken 1 with load factor 1. Earthquake load is also taken with load factor 1. Live load is taken multiplied by this factor lambda, which is actually less than 1. So it is a fraction. So in case of live load, we are taking only a fraction, and that fraction is 0.3 and 0.6. So that I will explain later from NBC. So this value of lambda is less than 1, it is 0.3 or 0.6. It is different than the Indian code. If you compare with the Indian code, here there is no load factor for E, earthquake load, whereas in IS code, there is a load factor of 1.2 and 1.5. Two load cases are there, 1.2 dead load plus live load plus earthquake load, and 1.5 dead load plus 1.5 earthquake load. Okay, so actually the governing case is 1.5 dead load plus 1.5 earthquake load, not 1.2 dead load plus live load plus earthquake load. So this 1.5 factor is actually converting the zone factor. It is not really a load factor, it is a correction factor, because the zone factor which has been adopted in Indian code, that does not correspond to DBE or MC. When you multiply it by 1.5 load factor, then it becomes MC. So if you compare the zero period acceleration corresponding to DBE from Indian code, then for zone 5, which is closest to the Nepal hazard, you can see that will be 1.5 into 0.36, that becomes MCE, and then from MCE to convert to DBE, it divides by 2. So relationship between MC and DBE in Indian code is 1:2. So DBE is half of the MC. At some places like in US, that relationship is 1/1.5. So that's why there, if you see, it is the relationship to convert MCE to DBE is 2/3 or 1/1.5. In Indian code, it is 1/2. So that comes out to be 0.27. This 0.27 is to be compared with the zone factor given in Nepalese code, 0.25 to 0.4. So we can see it is quite reasonable. Actually, it is a common understanding now that the zone factor given in Indian code is on lower side. So the revised Indian code, which is going to come soon, there also it will be upgraded. What will be the value? I do not know, but it will be, the maximum value will be somewhere between 0.3 to 0.4. In that range, it is going to come. So that will also have matching values with this. So these values which have been adopted in this revised Nepalese code may appear larger to the designers, that 0.4G is much larger than the previous which you were using corresponding to zone 4 or even zone 5 from the Indian code. That was only 0.27. So 0.27 to 0.4, there appears to be a jump. But please be assured that this is a more reasonable value. Okay, this is more logical value which is adopted in Nepalese code. I can understand a lot of problems must be going on currently because the zone factor has increased, the shape of the response spectrum has been changed, and when you are considering both the effects, the forces on the buildings will be increased tremendously. The design forces which will be coming on the buildings now, as per this revised NBC, will be much higher than what you will get from Indian code if you are applying there. And these values are more reasonable, let me tell you. The values which are coming from Indian code are on lower side. And soon Indian code will also be revised and these values will be updated. I do not know whether those will match exactly with Nepalese code or not, but those will be close. Then when we talked about earthquake, effect of earthquake is predominantly in horizontal direction, but that doesn't mean earthquake causes only horizontal acceleration. Earthquake causes both horizontal and vertical acceleration. Horizontal also in the two directions and then vertical. So all the three components are there. And in general, we should consider all the three components. So vertical component of earthquake is also important. Previously, the codes were not taking into account the vertical ordinate. Now in this NBC105 2020, the vertical component or this shape of the response spectrum, CV/TV. So TV is the period of structure in vibration in vertical direction. Okay, so this is period of vibration in vertical direction. There appears to be some error in this formula. It is given CV/TV 2/3/Z. So there is a general understanding world over that the vertical component of earthquake is roughly 2/3 of the horizontal, stronger horizontal component. So vertical component is 2/3, but in this formula, CV/TV is actually representing the spectral acceleration and Z is zero period acceleration. So here there should be CH/TV also. So that appears to be missing to me. I don't know whether some correction has come, maybe some amendment might have come, this might have been corrected for me, because this means that the response spectrum will remain constant, which is not possible. So what I feel that it should have been multiplied by CH also, which we are having in case of horizontal seismic coefficient. So that should also come. So please check and also discuss it with the code committee. They may look into it. There appears to be a typo error here. Okay, then as I said that in general, vertical component is acting on all the structures. And it is a good practice to consider the vertical component of earthquake in all the cases. In most of the cases, it will not affect the design. Okay, because in vertical direction, our structures are anyhow quite strong. I told you that in vertical direction, 1G acceleration due to gravity is always acting. And there is a factor of safety of 1.5 to 2. So the capacity in vertical direction is very large and it is generally not affecting. But in some special cases, this can affect. And when we are having long span roofs or bridges, there it is important. Where the span is more than 20 meters, their vertical component can affect. When we have this horizontal cantilever span of greater than 5 meters, if I am having a balcony, then also the vertical span is important. Sorry, this vertical component of earthquake motion is important. And when we have pre-stressed components in horizontal direction, then also we should consider the vertical components. And those beams which are supporting columns, you understand what does that mean? It means floating columns. So in the buildings where you are having floating columns, then the transfer girders or transfer beams which are supporting the column, those beams need to be designed for this vertical component also. There the vertical component can be important. And then in base isolated structures also, it is important. Now, if I have to calculate the design spectrum ordinate, so design spectrum will be calculated from the shape. As I told you earlier, CHT is representing the shape. It is the normalized shape. That shape needs to be multiplied by Z. And another factor is importance factor. Importance factor depends on the uses of the building. That what are the post-earthquake uses of the building, and is there any post-earthquake hazard due to that building? So that importance factor will come from there. I have written here, although it is not given in the code explicitly. So please see this note is from our side that here the Z is to be replaced by 2/3Z. Rest of it should remain same. So rather than what is given here that CV/TV is 2/3Z, the C in vertical direction should be equal to CHT. This CHT will remain same. Only thing is that in place of T, we will have TV, and this should be 2/3 Z. That's how it should be used, like we are doing 2/3 of the horizontal seismic coefficient in case of Indian code. In case of Indian code, we use Z/2 to convert MC to dB. I discussed that. And in case of NBC, the Z is defined for dB itself. The Z is not defined for MC. And this is again a better approach than defining MC first and then converting it to dB, because we need a factor to convert from MC to dB. Currently, Indian code uses a factor of 2, but that is controversial. Whether that factor is 2 at all the places or it is 2 at some places and 1.5 at other places. So that controversy is there. If we are giving the Z for dB itself, then it is okay. In fact, in Europe, this is the practice. Europe, if you look at Eurocode, in Eurocode, the hazard is defined for dB, but in American code, the hazard is defined for MC. So Indian code is similar to American code, and Eurocode is similar to, sorry, Nepalese code is similar to Eurocode, where the hazard is defined for dB. Then, if the earthquake is having all the 3 components, in design also we should take all the 3 components. Again, I will say that in general we should consider all the 3 components of earthquake together. But if the system, the structural system, is having orthogonal arrangement of lateral load resisting elements, what is meant by orthogonal system? This type of system where the beams are perpendicular to each other. So you can see, if I apply earthquake in X direction, the beams in Y direction will not be subjected to any force. Similarly, if I apply earthquake in Y direction, the beams in X direction will not be subjected to any earthquake force. But what about columns? So due to earthquake, there is not only the force in beams, there are forces in columns also. So for the design of the columns, it is important that we consider both the earthquake components. So I will recommend that whatever structure you are designing, please consider both the components in all the structures. But the code, Indian code as well as Nepalese code, allows us to ignore the other component in case of such systems which are having orthogonal beams and columns. Okay, so this is another orthogonal system where we have shear walls also. So when we are applying earthquake force in X direction, then the Y direction components will not be affected. But we have, if we have this type of members where the this type of building configuration where the members are not perpendicular to each other, all the members are not perpendicular to each other. So this is a non-orthogonal system, and in such non-orthogonal system, we should consider the component of the other component of horizontal component of earthquake also. So for example, X and Y, these are the 2 horizontal components, and Z is the vertical component. So in case of orthogonal system, the code says that we should consider dead load plus this lambda times dive load, earthquake in X direction full, and 30% in Z direction. Why 30%? Why not full in Z direction? Z is the vertical direction. Because if we look at the records of a single earthquake in 3 directions, we will see that those records are non-correlated. Non-correlated means that those are varying randomly. So when the peak is occurring in one direction, the peak in the other direction is not occurring. Other direction, it is somewhere below the peak. So that's why because the response spectrum, you have seen, we are plotting the peak response, and what we'll be reading from there will be the peak response in X and peak response in Z. So both the peak responses cannot occur simultaneously. That's why we are taking one response as full, other response as 30%. So in one combination, X is 100%, Z is 30%. In the other combination, Z is 100%, X is 30%. When we have non-orthogonal systems, and I am saying in case of all systems, you should use this, one of the component is full and the other 2 components are 30%. So first X is full, Y and Z are 30%, then Y is full, X and Z are 30%, then Z is full, and X and Y are 30%. So many combinations you have to consider for earthquake in different directions. Okay, then importance factor also appeared in our calculation. And as I said, that importance factor depends on the uses of the building, that for what purpose we are using the building. If the building is having some post-earthquake use, for example, hospitals, so hospitals will be required after the earthquake, because that's the place where our wounded people, the injured people will be treated. So hospitals, then fire stations. After earthquake, there are fires. Then for rescue and relief also, the fire stations are required, or people, fire brigade people are required. Power stations, so that the power outage is not there. Police headquarters to take care of the command and control after the earthquake has occurred. Then gas or petroleum distribution facilities. I don't know what is the situation in Kathmandu. Maybe there may be some proposal to have distribution of gas, the cooking gas, through pipelines. In metros in India, that facility has already come, and it is going to come. We are hearing that in Roorkee also this will be available. So it is good, it is very convenient, but it is dangerous during earthquake. So if it fails, if the pipeline ruptures, it will cause fire, post-earthquake fire. And that's why these need to be given special importance. Then those structures which are supporting or storing hazardous substances like acids, chemicals, toxic substances, which failure of which can lead to larger disaster. Those structures also needs to be designed giving more importance. So such structures are given assigned an importance factor of 1.5. Then normal structures are having 1, and some of the structures which may be required after the earthquake, but their functionality is not needed. So for example, schools. So schools will be used for giving the shelter to the people. Cinemas, assembly halls, because these are having a large gathering, and if these are failing, then failure of one structure will lead to large number of deaths. So that's why these are also assigned slightly higher importance as compared to ordinary structures. So it is in between. So nowadays apartment buildings are coming. So in one apartment building itself, there are more than 500 people. So in such buildings, we should have an importance factor of 1.25. This is more or less same in both the codes. So this is about the calculation, one aspect of calculating the earthquake force, that is hazard. How to define the hazard and how to calculate our seismic coefficient. Then another important issue in earthquake is the inelasticity of the structure. So we never design our structure to remain elastic during earthquake. So it is going to yield, and when it is yielding, it will have permanent deformation, or what we call plastic deformation or inelastic deformation. So the source of this inelasticity is from the material. Our structures, RCC structures mostly we are constructing, those are made of concrete and steel. Steel is known to be a ductile material. What is meant by ductility? That the force goes on increasing rapidly as the deformation increases, or the stress goes on increasing rapidly with strain up to a point. And at that point, the strain increases either with no increase in the stress or very little increase in the stress. So this phenomena is called yielding. So the point from where the strain starts increasing without increase in the stress, this is similar to flow of fluids. So what happens to the fluids? The fluids flow under a constant head. So if I provide a constant head, pressure head in a pipe, it will continue to flow. Or if I have an open channel flow and there is a gradient, mild gradient, which is causing a constant head. So under that, it will go on flowing. So after a particular stress, the metals start behaving like a fluid. Okay. So this property is called ductility. And measure of ductility is ductility ratio, which is the ratio of ultimate strain to the yield strain. And what you see here in case of mild steel, this ductility is maximum. And as you increase the strength of the steel, the ductility goes on reducing. And what happens? As the grade of steel is increasing, the ductility goes on reducing. And that's why there is a restriction on the maximum grade of steel which you can use. So we will be discussing that in the next talk, which we'll be having on next Saturday, when I will talk about ductility or ductile detailing, that what are the limitations in the two codes, IS13920 and NBC105. We will talk. But this is the source of nonlinearity in our structure. Then concrete itself is having nonlinear behavior. Unconfined concrete is very much nonlinear. It achieves a peak and then suddenly it drops its strength. It gets crushed. If we confine the concrete, then we can see we get a much higher strength and much larger ductility. But there is a lot of nonlinearity in this behavior as well. As a result, the structure which we are constructing, if I apply a force F and measure the displacement on any structure and plot the load displacement curve, the load displacement curve will be something like this. It will be linear initially, then here yielding will occur, and then it will become nonlinear. For simplicity in our calculation, we represent this actually nonlinear curve by a simple curve. That simple curve is made of two lines, and we call it bilinear idealization. Bi means two, linear means line. So we are representing it by two lines, bilinear. And this bilinear representation is done in such a way, bilinear idealization is done in such a way that the area under the two curves is same. Why we are interested in area? Because the earthquake, which is causing shaking of the building, is actually imparting some energy to the structure, and the structure has to dissipate that energy. If a structure can dissipate that energy at the same or higher rate, it will be able to survive that earthquake. But if the structure is not able to dissipate the energy at the same rate, then we can see that energy will get accumulated. The displacement of the structure, the deformation of the structure will go on increasing, and finally it is going to collapse. So energy dissipated or work done on a structure depends on or is given by the area under the load displacement curve. We are aware with that. So that's why this load displacement curve, area below the curve, we keep same when we are doing a simplified representation of the actual curvilinear load displacement curve, because this makes our calculation simple. Now, another property is elasticity of the structure. So in the initial range, till the structure is loaded with stresses much less than its yield stress, then the loading and unloading path are same. So if I load this structure here and unload it, it will follow the same path. It will come back to the original condition. When I remove the whole of the load, the displacement will also become zero. So that's why this type of structure we call elastic. It has no permanent displacement. It is having the same loading and unloading path. But what happens after yielding? The situation changes. If I start unloading now, if I have loaded it up to this and I start unloading, it will not go back on the same path. Rather, it will follow this path. So it will come here. And you can see here, even when the load is zero, so load will be zero at x-axis. So when this curve reaches x-axis, the load is zero, but the displacement is not zero. There is a permanent displacement. This displacement we call inelastic displacement or plastic displacement. And if I want to reduce the displacement, that permanent displacement, I have to apply the load in the opposite direction. And then if I reverse the loading, it will follow this type of behavior, which is cyclic, which is hysteretic. In general, if I have, let us say, a structure, a well-detailed steel structure, which is quite ductile, then the loading or load displacement behavior under cyclic loading will be something like this. So it will have cyclic behavior and it will form hysteretic loops. And these hysteretic loops are representing the energy dissipated by this structure per unit or per cycle. So larger the area of the hysteretic loop, more energy it is able to dissipate. So if I want my structure to resist a larger earthquake, its hysteretic loop area should be larger. And how we can increase the hysteretic loop area? One way is by increasing the displacement. So if the displacement is more, then we can see larger hysteretic loop will be there and the energy dissipated will be more. The other possibility is that I keep the displacement same and increase the strength. So if I increase the strength here, then also the area of the hysteretic loop is going to increase with same displacement. So both ways I can enhance the energy dissipation capacity of my structure so that it can survive a larger earthquake, either by increasing its strength or by increasing the plastic deformation capacity of the structure. Because if at a given strength, the earthquake is giving a lot of energy to my structure and its hysteretic loop is increasing, and this increases beyond the ultimate displacement capacity of my structure, then it is going to collapse. So I have to limit the displacement within the capacity of the structure. Otherwise, the structure is going to fail. So to avoid that, I have to provide adequate strength so that the area of the hysteretic loop is sufficient to dissipate the energy imparted by the earthquake within the specified displacement. So this can be represented by the simple analogy, a simple illustration I have. Suppose I have a hypothetical structure. That hypothetical structure is very strong. It is having very large strength and it is not going to yield during earthquake. It is not going to fail during earthquake because even yield during earthquake. So its behavior will remain linear elastic. So this is the linear elastic behavior. The force acting on my structure is, let us say, VE, and the displacement which I am getting is delta E. So elastic force and the corresponding elastic displacement, these are related with a line. And this is a hypothetical structure. Why I'm saying hypothetical? Because we never design our structures to remain elastic during earthquake. Rather, our structures yield at some value of Vy. And what is this Vy? This is this point where the two lines in our idealized curve are meeting. So this point is not on the actual load displacement curve. This point is a notional point which is lying on these bilinear idealized curve of the structure, load displacement behavior of the structure. So it will yield here, and what will happen? After yield, the load displacement curve will become flat. The displacement is increasing, but the load is not increasing. And a very interesting observation have been found by researchers doing or analyzing a large number of structures. They have found that whether it is a very strong structure, hypothetically strong structure, or it is a yielding structure, inelastic structure, the maximum displacement remains same. So this displacement, maximum displacement, is same as delta E, because whether it is an elastic structure, hypothetical structure, or it is a real structure which is yielding, the peak displacement will be same. Delta M will be equal to delta E. And this ratio of V and Vy, this we represent by R mu. So this is R mu, response reduction factor due to ductility. And this R mu is defined as the ratio of V by Vy. And from similar triangles, we can see that V by Vy is actually delta E by delta Y. And delta E by delta Y, delta E is same as delta M. Just now we talked about that observation which we call as equal displacement principle. So equal displacement principle says that delta M and delta E are same. So I replace delta E by delta M. So then it will be delta M by delta Y, and delta M by delta Y is the ductility. Okay, so demand ductility on my structure, mu. So R mu is equal to mu. So equal displacement principle suggests that R mu is equal to mu. That means I can afford to reduce the forces on my structure by a factor equal to the ductility ratio of the structure. And this phenomena is valid for long period structures. So actually it is valid for long period structures. In case of short period structures, the situation slightly changes. In that case, the delta M is not equal to delta E. Rather, delta M is larger than delta E, such that the area under the two curves, area under this hypothetical load displacement curve and area under the real load displacement curve is same. And if this area is to be kept same, then we can see delta M is greater than delta Y. And to keep the area same, we can again calculate this R mu, ratio of VE into VY, with using some geometry, and we get this relationship, square root 2 mu minus 1. And in this case, the R mu is less than mu. Square root of 2 mu minus 1 is less than mu. So R mu is lower than mu, but still it depends on mu. It is function of mu only, and mu is the ductility ratio here. So the response reduction factor which we get in our structures are depending on the ductility in the structures. Using this principle, which we call equal energy principle, we get R mu is equal to square root 2 mu minus 1 for short period structures. For long period structures, R mu was equal to mu. Using equal displacement principle, in case of short period structures, and by short period structures, which structures we will call short period? Those structures which are lying in the velocity control range, those are called short period structures. So as per Indian code, those structures which are having period less than 0.7 seconds, those will be called short period. As per Nepalese code, that period will vary depending on the soil also. So in case of stiff soil or rock, the structures which are having period less than 0.5 seconds, those will be called short period. But in case of very soft soil, those structures which are having period even up to 2 seconds will be called short period structures. So for short period structures, this is the relationship for R mu. Now, what is our current philosophy? Taking into account this factor that the energy dissipation takes place during earthquake, we first try to determine the demand as realistically as possible. So this is the design response spectrum. This blue curve is showing the design response spectrum, and this red curve is showing the hypothetical structure. So the hypothetical structure, the demand will be equal to this much. Okay, so this is going to be the demand on our structure if it was hypothetically designed for very high strength to remain elastic. So the elastic forces on our structure will come from the response spectrum directly. Then what we do, we reduce these factors by R, and we design for this reduced force. This reduction is by this factor R. And when we are designing our structures, we use limit state method. I think in Nepal also we are using limit state method. So we are using some partial factors of safety on material, and we are using characteristic strength or specified strength, which is 95% confidence strength, whereas the realistic strength is given by the average strength. The most probable value of any quantity is its mean value. So the probable strength of my structure is its mean strength, and mean strength is higher than the characteristic strength. Mean strength is characteristic strength plus 1.64 sigma, where sigma is the standard deviation. So because of these two regions, the actual strength of my structure is going to be higher, and that higher strength will be given by this curve. So the curve which you see here, this light blue curve, this is the actual strength of my structure. So the capacity is given by this blue curve, the demand is given by the dark blue curve. So you can see that even considering this higher strength, which we represent by overstrength. Okay, so this ratio between the actual strength and the design strength, this we call overstrength, and this is represented by omega. So omega is representing the overstrength, which takes into account the partial factors of safety and the difference between the characteristic strength and the average strength, mean strength. Then the response reduction factor R is equal to R mu into omega. What is R mu? R mu is the same which I have told you earlier in the previous slides. R mu is equal to mu or square root 2 mu minus 1. So that is R mu, and that is multiplied by this omega over strength. So we take into account the over strength also. That together gives us R, and R is giving us the factor by which I should reduce the force on elastic structure. So our calculations will go like this. First, we will estimate the force which is occurring on an elastic structure, because that is very easy. How I calculate that? I simply read the spectral acceleration from my response spectrum and multiply that by the mass or weight of the structure, and then I will get the total force acting on my structure. So total force is given by base shear. So base shear I can obtain simply dividing that elastic force by this response reduction factor R, and this response reduction factor R consists of R mu and omega. Now NBC defines R mu and omega explicitly, separately. R mu and omega are defined. Indian code gives the value of R, which is actually multiplication of R mu and omega. So if we are comparing this R, we should compare it with the product of R mu and omega. And in NVC, two values of omega are given. One for ultimate limit state, which is denoted by omega u, and another one for serviceability limit state, which is given by omega s. Now, this is the table. Some of you might have already seen. So values of R mu and omega u and omega s for different types of structures are given. So it is given for moment resisting frames, braced frames, structural wall systems, and dual systems. Some of the common systems I have done a comparison here. So the common systems are, first of all, a RC building, which is a special moment resisting frame. So this RC building, a special moment resisting frame, value of R mu is 4 and omega u is 1.5. So product is 6. So this product is to be compared with the R value given in Indian code, which is 5. So here we can see that the NBC is allowing larger, slightly larger, 20% larger reduction. Okay. So in many things it was conservative as compared to Indian code. In some things it is slightly, not much, slightly non-conservative. If it is a steel building, then also it is same in both the codes. So 6 in Nepalese code and 5 in the Indian code. Then special shear walls. This is important. If I'm having a building made of shear wall, and those shear wall are detailed for ductile reinforcement, then R mu is 3, omega u is 1.3. This comes out to be 3.9. In Indian code, it is 4. It's very close, 3.9 and 4. Similarly, RCC frame with shear wall, dual systems. So this is another common system, I think, in both the countries. So where we are having frames along with shear walls. When we are going above 10 story, usually we provide shear walls also. In that case, the Nepalese code is giving us a factor of product as R mu and omega u as 4.9. Indian code is giving 5, so very close. Then buildings with special concentric braces, steel buildings. Here you see the Nepalese code is somewhat conservative as compared to Indian code. In steel buildings, it is conservative. In RCC buildings, it is either matching or slightly more economical. There. Similar comparison has been done for masonry buildings also. So in masonry buildings, you can see that this is more or less comparable. So both the codes are giving similar, because this this response reduction factor for masonry buildings are perhaps not available. As far as I understand, in any other code, it is not available. So when they were developing the Nepalese code, they must have also tried to tally it with the Indian code. So it is very close to the Indian code. Now, that completes our behavior of the structure towards calculation of earthquake forces. Now, for method of analysis, we need to understand the dynamic behavior of the structure. And for understanding dynamic behavior of a structure, I will just give you an overview of some topics which are important. And one such topic is modes of vibration and fundamental period. This is important. So every building or every structure for that matter is having some natural modes of vibration. When we say that a structure is vibrating in a natural mode, or which mode of vibration is the natural mode of vibration. So these are the characteristic deflected shapes. And when the structure is vibrating with these characteristic deflected shapes, then all the mass particles on the structure are vibrating with the same frequency. That means those will be vibrating together. If one particle is starting vibrating, the other particle will also start moving. So these will attain their zero position simultaneously. These will attain their maximum position also simultaneously. So this is called natural modes of vibration. And number of natural modes of vibration in any structure are equal to the number of degrees of freedom in the structure. And each characteristic deflected shape is also called mode shape. You can understand it like this. Suppose I have a two-story building. In this two-story building, the displacement here is U1, here is U2, denoted by U1 and U2. And if it is given any displacement and left to vibrate, it will vibrate like this. So the two masses do not have any correlation. For example, here at B location, one mass is at peak, the other one mass is 0, the other mass is at peak. Here we can see that one mass is closer to the trough, the another mass is almost 0. So there is no correlation between these vibrations. Both the masses are vibrating in an uncorrelated manner. On the other hand, if the structure is vibrating in fundamental mode like this, then you can see that both the masses are vibrating in phase. Okay, when one mass is reaching the maxima, the other mass is also reaching the maximum displacement. Peaks are occurring together, troughs are occurring together. Okay, so this is our fundamental mode or first mode of vibration. And all the masses, in this case two masses, both the masses are having the same period. You can see here the period is same. Okay, so with the same frequency or same period, these are vibrating. Now let us see the second mode. In case of second mode, if you see U1 and U2, still the frequency is same. Both the U1 and U2 are vibrating with the same frequency. But when one mass is having its peak, the other mass is having trough of the vibrational displacement. What does that mean? That one mass is going towards right, the other mass is going towards left. But the extreme positions and the central positions are attained simultaneously. So these are moving in opposite direction, but at the same time with the same frequency. So frequency of vibration is same. So this is also a natural mode of vibration, and it corresponds to the second mode, where there is one node here also here. What is the property of this node? That here no movement occurs. The particles, mass particles above this are vibrating towards left. The below this are vibrating towards right. But here the displacement is 0 at all instants of time. Okay. In the same manner, we can have third, fourth, and fifth mode, which goes on increasing. Now, why we are interested in these modes of vibration? Because these simplify our calculation drastically. In reality, we will be designing multi-story buildings. Multi-story buildings are multi-degree freedom system. Their response is quite complicated. I have to solve that using computers, and with computers also it will take a lot of time. So this solution can be simplified a lot if I make use of these multi-degree freedom systems, multi-degree freedom system vibrations of modes. So response of a multi-story building can be thought of as the response of a number of single degree freedom systems. So this multi-degree freedom system has several, or this multi-story building has several modes of vibration. As I said, that this is the first mode. The second mode, part of the stories or some of the stories will be going towards left. Some of the stories will be going towards right. This is the third mode. Here you can see the stories are moving in opposite direction in 3 segments. So in the lower segment towards right, then in the middle segment towards left, and in the top segment again towards right, and so on. How many modes we will have? The number of modes will be equal to the number of degrees of freedom. But in case of buildings, the significant modes are there in the horizontal direction only, because there are so many degrees of freedom. So out of those, the floor degrees of freedom, if I take, so the number of modes is actually equal to the number of stories in each direction. If you perform a frame analysis, you can get more than number of stories. But here, some of the modes are not having much contribution. Further, the contribution of these modes goes on decreasing as we move from lower to higher modes. And these modes are such that this first mode is having the longest period, then the period goes on reducing. In fact, we define first mode, second mode, and third mode simply in the order of frequency. So first mode is having the lowest frequency, then the next higher frequency we call second mode, next higher frequency we call the third mode. So these are the increasing frequencies, and increasing frequency means reducing period. So these are the shortening period. The first mode is having the longest period, the second mode is having shorter period, the third mode is having even shorter period. Okay, so I can represent each mode by one single degree freedom system, and then what I can do, 4 methods are possible for analysis. The first method of analysis we call linear static procedure. So all the codes revolve around these 4 methods. Okay, and in different forms, these are giving these 4 methods. So these 4 combinations are possible. The first one is linear static procedure. In linear static procedure, we consider single mode analysis. We consider a single degree freedom system. Okay, rather than considering number of modes, we are considering only one mode. So the behavior of, or the response of the multi-story building can be obtained from the response of a single degree freedom system. That is the assumption. So that we call equivalent static procedure. And linear if the load displacement behavior is assumed to be linear. Okay, now we know in case of earthquake, linear load displacement behavior does not remain linear. It is non-linear because earthquake force is much larger. But what we do, we make use of that equivalent phenomena in terms of the response reduction factor, which we have obtained, R mu into omega. So we make use of that. So what we do, we actually obtain the response of the linear structure, elastic structure, which will give us much larger forces. And those forces I reduce by that factor R, which is equal to R mu into omega. So I reduce by that factor. And that's how I use the linear analysis itself for obtaining the earthquake forces. So because I'm using here a single degree freedom system, that's why we also call it single mode analysis. And the single degree freedom system corresponds to the fundamental mode of the structure. And once I obtain the total force, which is given as the base shear, I can distribute it along the height. And the distribution along the height is in proportion to the mode shape. So according to the mode shape in that fundamental mode, we are distributing along the height. This procedure we call linear static procedure or equivalent static procedure or single mode analysis. And this is a very simple method. We can use response spectrum to read the response of the single degree freedom system directly, and then we multiply and divide by some factors, and we get the response of the actual structure, which is nonlinear and also multi-degree freedom system. Our real structure will be having nonlinear behavior, and it will be multi-degree freedom system also. Here we are representing it by linear as well as single degree freedom system. Then the next more sophisticated method is linear dynamic procedure. In linear dynamic procedure, 2 possibilities are there. I can, okay, so this is representing our linear static procedure. What we are doing here, the response of the single degree freedom system, I can read directly from the response spectrum. if I know the period, and this period, this is the fundamental period of the building, from where it is coming, this can come either from analysis or it can come from the empirical formula given in the code. So both the codes, Indian code as well as Nepalese code, give empirical formulae for calculation of the period. Okay. Then the next method, which I was calling as the linear dynamic procedure. In linear dynamic procedure, two possibilities are there. One possibility is that I analyze this building to the ground motion applied here, considering a multi-degree freedom system. In multi-degree freedom system and single degree freedom system, what is the difference? That the mass and stiffness in a single degree freedom system are scalar quantities. These are given by single value. Whereas in a multi-degree freedom system, these are given by matrices. So I get stiffness matrix, mass matrix, and damping matrix. I can solve that equations in terms of matrices directly, and that we call linear time history analysis. Okay, so I can perform a time history analysis directly over the structure. Alternatively, what I can do, I can consider the different modes or the single degree freedom systems corresponding to different modes of the building, apply the same time history here, and get the response of each of these time histories. Okay, and then I have to just add these time history responses in all the modes, and that will give me the same response as here. So if I add those together, I will get the response of the building, and there is no error here. There is no approximation here if I am considering all the modes. Okay, but we know that the contribution of the higher modes is very small. So to save our time, what we can do, we can consider only few initial mode, and I can get the response of those, and I can sum that up. I will get very close to the actual response, which will come from the analysis of the simultaneous equations of motion of this multi-story building. So here there is no approximation. I will get the correct results. Alternatively, what I can do, I can use response spectrum. So if I want to determine the response of this building for a given response spectrum, in our codes, it is not the time history. What is given there are the response spectrum. So response spectrum, same response spectrum, I can obtain the response of this single degree freedom system, this single degree freedom system, and this single degree freedom system, and that response I can combine. Okay, only thing is that response spectrum is giving us the response of the single degree freedom system, not with time, but the peak value. So I will get the peak value of the response of different single degree freedom system. Again, the peak response of these single degree freedom system is also not occurring simultaneously. Earlier, when I was adding the time histories, then there was no problem. It will be added properly. Okay, corresponding values at that instant of time will be added. But if I want to add the peak values, then you can see that these peak values are not occurring together. So it is not advisable to add the peak values together, because that will be too conservative. That will be too high a response. Rather, what we do, we use two combination rules, SRSS and CQC. SRSS is a simple rule. In SRSS, what we do, it means a square root of sum of squares. So suppose the force in first mode is F1, in second mode it is F2, in third mode it is F3. So what I have to do? I have to simply do square root of F1 square plus F2 square plus F3 square plus so on. So that is SRSS. CQC is slightly more involved procedure, which you can either find in the code or in the book. In software, you will have option for both. So it's up to you. So if the building is having well separated modes, that means the periods T1, T2, T3, etc. are different, at least 15% different from each other, then you can use SRSS. But if these periods are very close to each other, or any two periods are close to each other, then you cannot use SRSS. In that case, you should go for CQC. The third method, which I told, is the time history analysis, which is direct integration of the simultaneous equations, and we get the response at each floor level. Okay, here this is the most rigorous method. All the modes contribution are inherently considered. This is very sophisticated. The problem is in selection of time histories, because the codes provide response spectra. Codes do not provide time history. That's a big problem. So which time history I should use? That is the challenge. And we need skill in selecting. There are methods by which, there are procedures by which we should properly select the time histories, which should be applied on my structure. Getting the response spectrum is very easy. That's why most of the designs are done using response spectrum. Okay. Then, even if we want to use the simplest method, the equivalent static method, linear static procedure, I need to calculate the period. That period can be obtained either by performing free vibration analysis in the computer model. So I can make a computer model and make free vibration analysis, or I can use Rayleigh method, a simplified method based on stiffness and mass matrices, but this is simplified method, or I can use empirical formulae. Empirical formulae are given in the codes. Those can also be used. There is a difference between Indian code and Nepalese code here, that Nepalese code allows an increase in the empirical period by 25%. So a 1.25 amplification factor is allowed by Nepalese code. This is similar to American code, but Indian code does not allow any amplification factor. And as a result, okay, usually what happens that this empirical period, which we are calculating using the formula given in the codes, those are much shorter than the periods which you will be getting from ETABS or any other analysis, computer analysis. So the computer model analysis gives us longer period, whereas the empirical formula gives us shorter period. So when you are calculating the design base shear, the empirical formula will give you much higher base shear than what you are getting from the analytical method. Both the codes, Indian code as well as Nepalese code, they ask that we should not design our buildings for base shear lower than what we are getting from empirical formula. That means all the member forces which I have obtained from analysis, computer analysis, those needs to be scaled for this base shear. So those should be increased in such a way that the total base shear is this much. So these needs to be amplified. Those needs to be scaled. Commonly in Indian code, we call it BB bar by BB correction. Same thing is there in NBC105/2020 also. NBC105/2020 says that lower value among the two, that means those which are calculated using analytically, or those which are obtained using empirical formulae, lower of the two. And as I said, invariably it will be the empirical formula which will be lower. So we have to use that value. Then in Rayleigh method, we can obtain the period using this simple expression. What is here? What we do that we determine the displacement of the structure under its gravity load. So imagine that if I have a building, I tilt that building by 90 degrees. So what will happen if I tilt it by 90 degrees? It is going to deform, okay, under its own weight. That deformation is represented by DI. So DI is representing that. WI is the weight or mass, which is there at that particular floor, and FI is the force. So actually, if we are analyzing it under gravity load, WI and FI will be same. So what you can do is, you can do an analysis in such a way that W times force, M into G times force, is acting at each floor level in the horizontal direction. And then you calculate the deflected shape. That deflected shape will give you DI. And then using this formula, you can calculate the period. So it is an approximate method, but it gives very close estimate. And we have a problem also. We have done a problem also, and I will show you there that how this period is calculated. Then there are empirical formula in NBC as well as Indian code. The form is like this: 1.25 kT into h to the power 3/4. So kT, this is the constant which varies from building type to building type. In Indian code, there are other formulae also which may be much more stringent. So you will see that Nepali code, which were quite stringent, which was giving much larger forces, much larger hazard value. The value of SA when we were calculating, that was much higher. But here it is not that stringent. Indian code is more stringent in this aspect, and that's why it's more or less compensated. So although it is designing for lower hazard value, but there is a lot of overstrength, and because of that overstrength, it performs well even under the real hazard value. Okay, so if we compare these empirical formula for period with IS1893, so here KT is given 0.075 for RCC frame, 0.085 for steel frame, and 0.080 for composite frame. In IS1893, these values are slightly different, and NBC uses 0.05 empirical coefficient KT for all other types of structural walls, whereas in Indian code, there is a formula 0.9 H by square root D, which is quite conservative, which gives very short periods. Okay. Then while calculating the earthquake forces, we consider the full dead load and a percentage of live load. And that percentage of live load depends upon the occupancy type of the structure. If it is a storage facility where we are doing some storage, that means where the permanent component of live load is more, we take this factor as 0.6. And for normal residential buildings where the permanent component is less, we have this factor as 0.3. In Indian code, it is 0.25 and 0.5. Okay. Now we can sum up the procedure. We have understood all the background concepts. So if I have to calculate the base shear on any structure using equivalent static method, I can obtain it like this: CD at the fundamental period into W. And how we will get CD? CD will come from CH, Z, I, and this is giving us the force on an elastic structure. We need to obtain the force on real structure. So real structure force will be this much, which will be CT1 divided by R mu into omega mu. So C was on the elastic structure. I divided by R mu into omega mu, then it becomes the real structure, which is inelastic, which is going to yield where we can reduce the forces. So there is a reduction force in the reduction factor on the force. Then we can substitute this expression. So here, if I substitute for C was CHT1 Z into I. So if I substitute that, I can calculate the shear force like this. These expressions are there in the code. You must be knowing these already. Then the shear force which I am getting from here, suppose I am using the period which is coming analytically, that needs to be scaled for the shear force which I am getting from the equivalent static method using the empirical formula for period. So VES is based on the empirical formula, and VMRS, it may be either using response spectrum method or any other method, but it is coming from analysis. Analytical period is considered here. So the shear force needs to be increased by this scale factor, and scale factor is this much, and all the member forces will be multiplied by this scale factor. If you compare it with the IS1893, in IS1893, the base shear is given as Z by 2, I by R, SA by G into W. Okay, so SA by G in IS1893 is equivalent to CH, and when you multiply it by Z by 2, it becomes equivalent to CD, and R here is equal to R mu into omega U, and Z in NBC corresponds to DB, design basis earthquake, and that's why here there is no reduction. But in Indian code, this is corresponding to MCE multiplied by 1.5 factor. So to convert this into DBE, a factor of 2 is used. So both are on the similar lines. Only thing is that the notation is different. The system of constants which we are using here are different. So that we have to choose accordingly. Then the next important parameter which we need for design, one is the force. Force comes from the base shear. Then other important parameter is displacement. There are checks on displacement also. So in Indian code, whatever displacement you are calculating from the design, the same displacement is checked for the drift limits. But in NBC, in the Nepalese code, the design displacement is obtained from the calculated displacement, multiplying it by factor R mu. Okay, so the displacement is the calculated displacement into R mu, and the drift is displacement divided by, so the drift is nothing but the ratio, okay, interstory drift ratio. So this is displacement divided by height, and there is limit given on the interstory drift ratio. So in Nepalese code, this drift ratio is 0.025. On the other hand, in Indian code, this limit is 0.04. You may be confused. How can this be so different? It is 0.025 here, it is 0.004 here. Actually, what is given in Indian code is corresponding to the design load. That means the reduced, at the reduced load. So the displacement is also reduced. But you recall equal displacement principle. As per equal displacement principle, the forces can be reduced, but not the displacement. Displacements are same. So by the factor by which we have reduced the forces, by the same factor, we have to multiply this displacement so that the displacement of elastic and inelastic structure is same. So we have to multiply it by R. So when we multiply it by R, this becomes 5. Oh, sorry, R is equal to 5, this becomes 2.02. So 0.02 versus 0.025. So here the Nepali code is less conservative. Then another problem which I see with Nepalese code currently is that actually this design drift, sorry, this calculated drift should be multiplied by R, which is R mu into omega mu. Whereas here only R mu has been used. Again, this appears to me a typographical error. I don't know whether this is intentional, there is some basis for it, or it is just they have missed it. I feel that it should be multiplied by omega u also. And I'm not sure, I'm not aware actually that whether any amendment regarding that has come or not. I also feel that if we are using only R mu, then this limit of 2.5% is very large. Okay. In American and European code, this varies from 1% to 2%. In that range, it is there. 2% is also maximum limit, which is there in Indian code. But here, this 2.5% limit is given, and that too multiplying with only R mu. Because if omega u also be used, that is something like 1.5 or 1.4. So it will increase by another 50%. Okay. So that is too flexible a structure. Such flexible structure should not be allowed. I don't know whether there is some thinking behind this. They have thought about it and then did it like this, or it has been missed somewhere in typography. So this should be multiplied by omega u also. Okay, as it is there in Indian code. So whatever factor we are using for reduction of forces, the displacement should be amplified by the same forces so that we get the displacement which will actually occur during earthquake. So the reduction is done by R mu into omega u. You know, R mu into omega u. So multiplication of displacement should also be by the same factor. Okay. Then the Nepalese code also defines the serviceability limit state. In serviceability limit state, the CD is obtained just dividing CS by omega s. There is no R mu here. Why? Because the name itself suggests serviceability condition, serviceability limit state. So serviceability means the structure should remain in service. There should not be any damage. Means we are not allowing our structure to yield. And if the structure is not yielding, there will not be any energy dissipation. There will not be any reduction. There will not be any ductility. So R mu or omega, sorry, R mu or mu will be equal to 1. and we will have only omega in this case. So in this case, R will be 1 into omega, that is omega. So omega S, and there is a separate column in that table for omega S. Omega S is also slightly lower than omega U. And then CS is considered as 20% of C at T1. Okay. So the serviceability earthquake is considered 1/5 of the DB. Okay, so it is not specified in the code which probability of accidents they are considering. Normally, we are considering 50% probability of accidents in 50 years, which corresponds to return period of 75 years. But that will not be 1/5 of this. That comes out to be roughly half of DBE. It is even lower than that. So it appears that this is 43 years return period, which is having 50% probability of accidents in 30 years. So that means it repeats itself on an average at 43 years. So roughly once within the life of the structure, that earthquake comes. So the earthquake, which we are more or less certain that it is going to come during the life of the structure, we should ensure that our structure will be serviceable during that condition. And what we have to check for the serviceability, we have to check the drift and no force check. So drift check is to be done, and the allowable drift is 0.6%. So it should be 0.6%. Again, you see the force we have reduced by 1/5. So if I multiply 0.6, it becomes 3%. So this is more flexible than the serviceability limit state at DBE, at ultimate load. Okay, and generally it will be the drift at the ultimate limit state which will govern. The drift at the serviceability limit state will usually not govern because this is higher than that. The force we are reducing by 1/5, and the displacement we are reducing more than, we are reducing less than that, 3 point something. Okay. Now we discussed these methods of analysis. So 3 methods of analysis are described in NBC. I have already given you the background of these methods. Once we calculate the base shear is distributed along the height using this formula in terms of floor load, and that floor load can be used to calculate the story shears, and then story shears will be used for design of the structure. Okay, the columns in the structure. I just want to show you an example which will give an overview of all this what we have discussed. So in this example, we are calculating base shear and floor loads for a 4-story building. So this 4-story building is having this plan, a simple plan, 3 bays in each direction, and the bay width is 4 meters, and the story height is 3 meters. So we will use 3 methods. The first method is that equivalent static method. So before using that equivalent static method, also we have to calculate the weight at different floors. So here the weight calculation is done, where we are taking also into account the percentage of live load. So we have assumed a residential building. In residential building, the live load is such that lambda should be 0.3. So that's why the 0.3 live load factor has been taken. And with that, the seismic weights at the first floor, second floor, and third floor, which are equal, have been calculated. And on the roof, it will be different. Why it will be different? Because we are having the walls and columns only below, and there is no live load also. So here it is coming out to be less than, slightly more than 50% of that at the lower floors. And then we have used the empirical formula given in the code. So it is a RCC frame building. So formula we can use, there is 25% enhancement allowed by the code. KT is that coefficient given in the code, which is 0.075 for RCC buildings, and 4 stories of 3 meter height, so 12 meter total height. This comes out to be 0.604 seconds. And then the base shear can be calculated using this formula. And for period of 0.604 second, let us consider soil type A. We can calculate the value of CH looking at the response spectrum, and this comes out to be 2.1445. We have to multiply it by Z and I and divide by R mu and omega u. So we calculate B like this, which comes out to be 1166 kilonewton. Then it is to be distributed along the height. The distribution is in proportion to the mode shape, and here mode shape is Hi to the power k, where Hi is the height of the floor. So for the first floor, height is H1, for the second floor, height is H2, H3, so on. And the value of k depends on the period of the structure. So period of a structure in our case is 0.604. From that table for interpolation, it has been obtained as 1.05. And if you use that 1.052, F4, F3, F2, and F1 can be obtained like this. And finally, you check that F1 plus F2 plus F3 plus F4 should be equal to shear force B, which we have calculated in the previous slide. Then in the top story, the shear force will be, you can see that the forces are increasing along the height. The top force is 357 kilonewton. In the bottom story, it is only 129 kilonewton. Bottom floor, it is only 129 kilonewton. But if you talk about the column shear forces, which goes on increasing towards the base, because in the top story, only the top floor load, which is 357 kilonewton, is acting. In the third story, these two will be added, and this becomes 768. And then below, the 3 floors will be added, and here all the 4 floors will be added, and that becomes equal to the base shear 116.69. Then the same problem we have solved using a simple method to calculate stiffness. What is that simple method to calculate stiffness? That we have assumed the beams to be rigid. That is an assumption. And if you assume the beams to be rigid, then the stiffness of the columns can be obtained as 4 EI by L cube. Okay. And Tajul, I think now I have got the error. Why I was saying that our period is coming out to be larger. The number of columns is not 4. The number of columns is 16, 4 in each direction. Or you have considered mass of only 1 column. Tajul? So 12 EI by L cube is the stiffness. If you are considering one frame, you will multiply it by 4. If you are considering the whole building, then you will take 16 columns, because there are 16 columns. And then this will give you the stiffness of 1 story. And then you can assemble the stiffness matrix of the 4-story building like this. You will get the stiffness matrix. So mass matrix is here, stiffness matrix is here. You can solve the eigenvalue problem. I'm sure at least some of you must have studied eigenvalue problem solution in a theory of vibration or a structural dynamics course, and the polynomial method has been used here. This will give us the frequencies omega square in different modes and the mode shapes phi. So omega square is giving us the frequency of vibration. So this is omega is 2 pi f. So it is a square of that omega, which gives us the eigenvalue. These we call eigenvalue and these we call eigenvectors. Eigenvectors are nothing but the mode shape. So first mode shape, you can see all the values are positive. In the second mode shape, half of the values are positive and then half of the values are negative. In the third mode shape, it is negative, then positive, then again negative. Here it is positive, negative, positive, negative. So if I plot these mode shapes will look like this. Okay. So these are the mode shapes. So you can see the first mode, all values are positive. In the second mode, there is 1 0 value. That means there is 1 crossover. In the third mode, there are 2 crossovers. And in the fourth mode, there are 3 crossovers. And the corresponding frequencies and the periods are like this. In the fundamental mode, we are getting the longest period. The first mode is also called fundamental mode. Here the period is maximum. And in the higher modes, the period goes on reducing. Okay, and we can calculate the modal seismic weight using this formula. We know the phi. So using these values of phi mode shapes, we can calculate the modal weights in each mode. For mode 1, this W1, W2, W3, W4. We can see that as the number of modes is increasing from first mode to second mode to third mode, the mass participating in that mode goes on reducing. In the fundamental mode, it is 8391 kilonewton. Whereas in mode 4, it is very little, 23. So you can see that as compared to 8391, you can even ignore W3 and W4 both. So if you consider W1 and W2, the two modes itself, themselves, you will have only little error. Okay. So the higher modes contribution goes on reducing. Then we can calculate VI using the formula which we have seen there for each mode, and for mode 1, 2, 3, and 4, it is calculated like this. You can see that the shear force reduces drastically. In mode 4, it is very close to 0. And the total base shear we can obtain by summing these up using SRSS. Keep in mind, we don't have to add these directly. The different modal quantities, whether it is force or base shear or displacement or moment or anything, we should not add directly, rather we should add using SRSS. So this comes out to be 671 kilonewton. Okay. Then we can distribute these base shears along the height in proportion to the same mode shape. So these mode shapes have been already obtained, and if I distribute according to this mode shape using this formula, then the forces comes out to be like this. So on the top, in the fundamental mode, we can see the maximum force is at the top and minimum at the bottom. It is gradually decreasing from top to bottom. But in the other modes, some of the forces are positive, some of the forces are negative. And if you obtain the base shear in different modes, story shear in different modes will be what? The forces in that mode added from top. So in the fundamental mode, at the top, it was maximum. Then in the bottom story, although the floor load reduced, but the story shear increased. So story shear is increasing towards the base. But same is not true for second, third, and fourth mode. In second, third, and fourth mode, it will follow an irregular pattern depending on the mode shape. Okay. So only in the fundamental mode, you will see that the story shear goes on increasing towards base. Here, it is not increasing towards base. It is not that you can get by summing up these two. So you will see that equilibrium is satisfied when you are considering the fundamental mode. In higher modes, the equilibrium may or may not be satisfied. So if you want to calculate the shear force at different in the different stories. So in the bottom stories, we have already obtained by summing up in different modes. In second story, the story shear obtained in different modes and summed up like this, and we can get it like this. You can see here we have got quite different story shear, and one of the reasons for this may be our calculation error in the stiffness, use of 4 columns in place of 16 columns. So that has given a longer period, and because of that longer period, our base shear has reduced. Okay. Now, same problem has also been analyzed using ETABS. So in ETABS, you consider the period obtained analytically, and what we obtained analytically, then it comes out to be 0.613, and from empirical formula, it came out 0.604. Okay, so here the difference is not much, but in some cases this difference may be large. And when we calculate the shear force using this formula, this period which has come from the analytical model, it comes out to be 1082, whereas from this empirical formula, this comes out to be 1166. So all the forces you are getting from ETABS analysis, those needs to be multiplied by this scaling factor, which is this empirical base shear divided by the analytical base shear. So this factor is to be multiplied. Okay. So that's the example which illustrates the procedure. Lastly, just 2 slides I want to show you regarding effective stiffness. So what happens in case of RCC structures? During earthquake, there is significant cracking and there is yielding of steel also. So what happens due to cracking? The effective stiffness of RCC members reduces. So we need to consider this reduction in stiffness due to cracking. This reduction in stiffness is good for calculation of displacement. It is on conservative side. But in case of forces, if the stiffness is reduced, so what will happen? The period will be increased, and when the period will increase, the shear force, the base shear is going to reduce. But that will be taken care of by this correction, BB bar by BB ratio correction. So this will be taken care of by this correction. Okay, so this is what is provided in NBC105, that in case of beams, the cracked section stiffness, we should take 35% of the gross stiffness. In case of columns, because in columns axial force is present, so the cracking will be less. So there it is 70%. In uncracked wall, sorry, it has been reversed. In cracked walls, it will be 50%, and in uncracked walls, it will be 80%. So in uncracked wall, it should be higher. In cracked walls, it should be lower. So please interchange this. This is cracked and this is uncracked. So 50% in case of cracked walls and 80% in case of uncracked walls. So, and in case of steel members, because there is no cracking in steel, we need not to reduce any stiffness. We have to consider the gross stiffness. Okay, thank you. That's what I wanted to discuss in this talk. In the second talk, which we will be having next Saturday, we will talk about the ductile detailing of RCC structures. Okay, so that will also take nearly about same time, 2 hours. We will discuss, and now we can take up your questions and queries.
Sure.
You might have written in the box.
Thank you very much, Professor. Thank you very much for the wonderful presentation. Actually, some participants were initially asking, like, how can an Indian professor know about the Nepali code? How will he present us about the Nepali code? And I'm confident that you have erased all those doubts. It was a wonderful comparison between the both codes. And I have also been your student for 2 semesters, and still you surprised me, because when one participant asked that will we be showing some detailed procedure how to calculate, I said no, professor will be giving some insights. We won't be showing any detailed calculation, but still this time we have presented all the detailed calculation as well by manual methods. So that is also surprising and very helpful to all the participants, I hope. And we have some questions in the comment section. So I'll be taking the questions. If I have any confusion regarding the question, I'll be asking the person who asked the question to unmute and ask themselves. So can I take the professor? Can I take the question, sir?
Go ahead. Yeah. We can take one by one.
Okay, so Anusha Baral asks, do you have time history data, sir, of Northridge and Loma Prieta? So how do you get the time history data of different past earthquakes?
Okay, so what I can do is there are several sites now available, websites, from where you can download any ground motion. Okay. So you may choose any criteria. In fact, when you are selecting ground motion, the ground motion data is so much that it will be difficult for you to choose which ground motion you should use. So now even the search, there are some tools available to search appropriate ground motions. I have prepared a list of different websites I can share with you. I will send it separately, which can be shared with all the participants here. They can look at those websites, and those websites will provide you any number of ground motions based on any criteria.
Sure, thank you. So next question is from Man. His full name is not written. So Man asks, sir, may I know more about how we take advantage of reverse cyclic nature of earthquake? How we take the advantage?
We take a lot of advantage. For example, you have seen we are first calculating the elastic force, and then we are reducing it by R, or R mu into omega u, and that value is roughly 5 or 6. In Nepalese code, it is 6. So we are reducing the force by 1 by 5 or 1 by 6. So we are designing only to 16 to 20%. So strength is only 60 to 20%. Remaining is energy dissipation. 80% we are depending on ductility or energy dissipation. 20% we are depending on strength. So that's why this energy dissipation or reverse cyclic nature of the loading, we are taking a lot of advantage. 80% we are taking advantage of that.
Okay. So next question is from Utkarsh Vetwal. What is the predominant frequency of the given design earthquake in NBC105? What is the predominant frequency? How will it ensure that there will be resonance to my building so that my building captures maximum response? How will it ensure?
Okay. So see, first of all, let us understand that in case of earthquake, the classical resonance does not happen, because for resonance, you need a harmonic input. A harmonic motion should be there. And it should be continued for some time. Then only the steady state will build, and resonance-like situation will occur when the response will build up. So that type of response does not, that type of resonance does not occur in earthquake. But if the predominant frequency of earthquake is closer to the predominant frequency of the structure, then the response of the structure will be large. The forces will be large, and that you can see in the response spectrum itself. So you can see in response spectrum, there is a peak which is varying from 0.1 second to 0.7 second or 0.1 second or even 2 seconds in some of the soils. So the predominant frequency depends on the site condition, and this is there already accounted for in the shape of the response spectrum. So you need not to worry. If you are calculating the forces using the response spectrum given in the code, this quasi-resonance, resonance-like situation which will occur. It is not resonance, but it is something similar to resonance which will happen. That will be taken care of by the response spectrum given in the code.
Yeah. So what if something like the Mexico earthquake of 1980? I think it was a pure sine wave type of earthquake. In
55. Yeah. So
if that kind of earthquake is there, then,
graph which I have shown, that was also sinusoidal. So, but if you are taking response spectrum, and you should see this Kathmandu also. Kathmandu is even more surprising that way. So that Kathmandu record. So there the period was, the predominant period was something like, if I remember, it was somewhere between 1 to 2 seconds. And here it is close to 5 seconds. So Kathmandu is in even one step far away, because the depth of that alluvium in Kathmandu is much more than even Mexico City, because that is a dried shore of the lake. So they were on the shore, not in the middle. And here there is a deep valley which has been filled by rivers. So the depth is very, very large in case of Kathmandu. So that
there are some chances.
we need to take into account. And here the chances of, and interestingly, there is one disadvantage where we are having very large amplification at 5 seconds. But what happened at lower periods, shorter periods,
less,
0.5 second or 0.4 second, the response spectrum reduced drastically. And that saved a lot of low-rise, not very strong buildings in Kathmandu. Otherwise, if it was on rock, perhaps the damage in Kathmandu would have been more if it was on rock. So that valley, at one stage, there was this, what was that apartment building? Horizon building, Horizon apartment. No? So Horizon apartment got damaged so badly. And at the same time, many of our not very strong buildings, I was surprised, many of mud buildings, those were saved. Why those were saved? Because their frequency was very different than the frequency of the earthquake, because of this very deep alluvium. And some people gave analogy of this by a rocking ship. So it is like a rocking ship. The whole valley vibrated with a very long period, very short frequency, low frequency and long period. So due to that, what happened? It was vibrating slowly. So those low-rise buildings, those were moving along with it without any effect. But those tall buildings, those developed more damage. So when you are designing a tall building in Kathmandu, you have to be very, very careful. Short buildings perhaps will be saved.
Okay, so thank you. I think that answers this question. So next is from Biswa Balla, sir. response spectra is subdivided as constant acceleration, constant velocity, and constant displacement. Is this characterization correct?
I mean, this is based on
Acceleration
observation.
control.
So this is based on observation, and world over it is seen like that. So if you take any earthquake and plot its response spectrum on tripartite graph, you will see that part of it is parallel to acceleration axis, part of it is parallel to velocity axis, and part of it is parallel to displacement axis. So that shows that there is a range which is controlled by acceleration, or what we call constant acceleration, then constant velocity and constant displacement.
So next, Tekan Pandit asks, how much is it logical to use DBE and MCE word in deterministic approach? The current
In
IS
deterministic,
2000.
in deterministic approach, there is nothing like DBE or MCE because there is no probability attached. Okay, there we use rather mean and mean plus 1 sigma. So in deterministic, we get a mean value, we get a standard deviation. So generally mean plus 1 sigma is considered corresponding to MCE, and mean is considered corresponding to DBE.
Yeah. So I think that was the question. So next question from Utkarsh Vetwal is, what is the load combination used for vertical earthquake according to NBC? Is it same as that of IS1893? So I think this was answered in the presentation. Like vertical
but it will be better to clarify. All the earthquake, whether it is horizontal or vertical, the load factor will be same. So in Indian code, it is 1.5. In NBC, it is 1.
So Biswa Balla sir asks, can you please comment on IRC SP 114 2018 seismic design of road bridges? I feel that it is very good document.
Yeah, it is very good document, no doubt about it, but for bridges, not for buildings. I have been using that also. So if there is a good number of bridge engineers in Nepal, we can do a separate talk on design of bridges as well, as per IRC. I don't know whether there is a separate code in Nepal for bridges. I don't think for bridges.
No, we follow IRC code mostly.
IRC you follow.
Yes, so we are using SP.
Now you have to learn how to use IRC along with NBC105, because hazard you have to use from NBC105. Hazard you cannot borrow from IRC. Earlier you were taking, because IRC is also taking hazard from IS1893.
Yeah.
So now you have to learn how to design your bridges considering hazard taken from NBC105. So maybe if people are interested, if we have number of people there, we can discuss that also on some day.
Yes, that will be a good idea, sir. So next, Tekan Pandit asks again, during the determination of R factor after the pushover analysis, some literature used 2R is equals to ductility into redundancy into overstrength by assuming overall 2R value. Actually is a response reduction factor, and some literature used R is equals to ductility into redundancy and overstrength. Which one is correct? Whether 2R or
actually
R?
it is R only, not 2R, because in Indian code we get Z by 2 into I by R. So sometimes people get confused and they consider 2R as the reduction. Actually 2R is not the reduction. Reduction factor is R only. So the ductility and overstrength should be equated to R, not equal to 2R.
So yeah, so I think he has added that here. So next, Utkarsh Petwal asks again, should we use load combination given for non-orthogonal system to design whole structural elements or only structural elements which are not orthogonal?
My suggestion is that for every structure, for every component, you consider 100-30-30 rule. Those components which are not affected by the horizontal other component will not be affected. Their design will not be affected. Wherever it is important, it will come into picture. So rather than spending so much of time and making errors on which component I should do, which component I should not do, give the instruction to the computer to use 100-30-30 in all the cases, in all the structures, all the components. In fact, in American code, that is the practice. They don't say that for this structure you use vertical, for this structure don't use vertical. All structures use 100 ELX, ELY as well as ELZ. Wherever it will be important, it will automatically come into picture. Where it is not important, it will not come into picture. So that is an easier approach.
So next, Adhikari Susan asks, is peak ground acceleration similar with seismic zone factor Z? Eurocode uses peak ground acceleration, whereas we use zone factor. Is there any specific reason? So why they have different words?
As I have shown, both are same. So when they say PGA, they also mean EPGA. Normally, when people are saying PGA in codes, it is not what is coming from the accelerogram, the peak of the accelerogram. That they do not call PGA. PGA also is coming from response spectrum corresponding to 0 period. So what I said as EPGA, they call that as PGA. So PGA, zone factor, EPGA, or ZPA, these are all same quantity. So all the codes are using same quantity, but calling them by different names. So these 4 or 5 names are of the same quantity.
So next, Tekan Pandit again asks, what is the logic behind to use load factor in seismic load in IS code? First, we use the load factor to increase the earthquake force, then reduce the same force by using R value. In which sense we first increase at the same time we decrease?
So first of all, what you have said is very right. It appears irrational. But let me tell you, what is given in the Indian code as the load factor is not really a load factor. That is a correction factor, because the zone factor, which is there in the current Indian code, that is based on DSHA, deterministic seismic hazard assessment, not probabilistic seismic hazard assessment. And this is the median value. So median value, mean value, when you multiply it by 1.5, then it becomes MC. So that 1.5 factor is not a load factor. That is to convert the DSHA value into equivalent MC. And then that is divided by 2 to convert this into dB, and divided by R to take into account the inelasticity. So there is no load factor as such.
So then Tekan Pandit has another question. Stiffness modifier only applicable for seismic load combination or also for gravity load combination? It is
not for gravity load, because in gravity load there is very little cracking. So the cracking in case of seismic load is much more. So these are for seismic load, not for gravity load. But there is a problem. When you are doing an analysis, you cannot have separate models for gravity load and earthquake load. So what usually we do, we make a model with these stiffness modifiers and perform gravity analysis and earthquake analysis both on the same model. In gravity analysis, what will happen? The deflection will be slightly more. In the forces, there will not be much difference, because the distribution of the gravity load depends on the relative stiffness, not on the absolute stiffness. So relative stiffness, there is some change. So there is some change in the relative stiffness also. When you are considering gross, it is 1:1. When you are considering crack section, it is 0.7 to 0.5. But the difference is not that much. So what you can do is, you can use, although theoretically it is not applicable, but practically it will not be possible to perform 2 analysis with different stiffness and then combining the results, which will be difficult. So you can go ahead with using same reduction factors for gravity as well as earthquake.
So Tekan Pandit asks again, this live load factor only used for, is live load factor only used for determination of base shear, or it is used for load combination also, DL plus percentage of live load plus EQ? Live load factor only used for base shear. Earlier IS code mentioned this live load factor also used for load combination, but recent 6th revision is silent about this.
I got it, what he's saying, I got it. So yeah, you are right. Earlier, the Indian code was, see, first of all, why there is a reduction in live load? When we are designing for live load in as per IS1875, IS1875 part 2 gives the live load. So we are specifying live load on a beam, let us say. So which condition we will consider? We will consider the extreme condition on that beam which can occur. Means there is overcrowding. We have stored something right at the top of that beam. And not only that, we are bringing a heavy furniture or a trunk and dropping it. So there is impact also. So when we are specifying live load for design, in gravity case, we are considering the maximum effect. That means overcrowding, overloading, as well as impact. But when we are designing the columns, then the columns of a lower story, the top story column, we can see that there is a possibility of dropping on the beams. But if a column is supporting large number of floors, several floors above this, then not on every floor people will be dropping simultaneously. That is not there. That's why even in gravity load design, there is a reduction allowed in the live load. So I do not know which code you people are following, but if you read IS1893 part 2, it says that if there is more than one floor supported on a column, you can reduce it by 10%, then 20%, then 30%, and maximum 40%. So 60% reduction, that means up to 40% load. You can go even under gravity load. In case of earthquake, what is happening? Same reduction will be applicable. And further, the inertia force will be acting only on mass component. It will not be acting on the impact part, because earthquake is inertia force. Then the furniture which is sliding or rolling, that will not transfer the inertia force to the building. So there it will be even less. So 40% reduction is there. That's why NBC gives it 30%, even less than that, and you can apply it uniformly throughout the height. In Indian code, due to some region that has been taken away, not purely technical regions, but that 40% still holds good, because there is nothing written in Indian code now about the live load which is to be taken in combination. Means whatever you are taking in the dead load plus live load combination, same you will take in dead load plus live load plus earthquake load combination. And in dead load plus live load combination also there is 60% reduction. So that we can do. And most importantly, if you compare dead load with live load, in practical design, you will see live load is nothing. So if you consider 25% or full, it is not worth the effort which you do in reducing it. So increase is just negligible. So if you consider even full live load, it's not going to affect your design.
Okay. Thank you, sir. So then there is a general comment from Biswaballa, sir. Thank you, Professor Singh, for going through NBC105 in such detail. Detailed comparison with IS1893 should be helpful for all structural engineers of Nepal. Okay, so then Sam Awal adds, is allowable drift in IS code 0.004 times R? So is there a multiplication with R?
Right. Because if you see the Indian code, IS1893, and see the minimum gap required between adjacent buildings. So there it is saying that you have to multiply by R. So when we are comparing the interstory drift 0.4%, we are not multiplying by R. That means it is corresponding to the reduced force. So the actual displacement is R times, and that also comes from equal displacement principle, which I explained, that the forces can be reduced by R, but the displacement are same. So if you have done analysis using reduced forces, displacement you have obtained corresponding to reduced forces, those should be multiplied by R. And that's why I feel that in NBC105, there appears to be a typological error, that reduction in forces is by R mu into omega u, and multiplication in displacement is only with R mu. So why not omega u is there? That should also be there. That's my doubt. So maybe I will discuss with Professor Dhakal and Professor Maski also. I will write an email.
So Suraj Gurung is asking, is it okay with response reduction value 5? Some of the research says 2.5 to 3. So how is the value of response reduction value factor determined, and is it high or low? How do we know?
That's another story. See, actually the response reduction factor should come from nonlinear analysis, because it depends upon the ductility. So it has to come from nonlinear analysis. But response reduction factor, those code committees were forced to give response reduction factor much before the nonlinear analysis could be done. So from where those poor people will bring? So based on their judgment, based on their understanding, based on their past experience, they have suggested some response reduction factors, which are continuing in all our codes. And now there are efforts to calibrate those response reduction factors with actual performance based and risk based design. And there the values are varying a lot. Okay, still there is also not a straightforward solution because nonlinear analysis is so complex and it depends so much on the user that different people come out with different values. So it is becoming very difficult to come out with a consensus that this should be the value of R. So still we are continuing with the wisdom of our ancestors who have somehow decided these magic values, and we are still using those.
So next is a question from Roshan Shrestha. While analyzing buildings, should we go for bare frame or infill wall? So is infill wall modeling compulsory or what we do? He's asking.
Indian code says, and that I see as a more rational approach, that we should perform two analysis, one with the infill wall and another with the bare frame, and whichever is giving the higher forces, that should be used. And we have seen that bare frame gives much higher forces than infill frame in most of the cases. One problem in this regard I see in NBC105, that is Indian code gives a separate period formula for infill frame. But in NBC, I do not see a separate formula. Only thing is all other, we have to take 0.5. So in place of 0.075, it is 0.5. But actual increase, actual reduction in period due to infill may be even much larger, much bigger reduction maybe there because of the infills. So that aspect needs to be seen. That our Indian designers complain a lot about that formula because it increases the base shear tremendously. But we have seen that because of this increase in the base shear only, our infilled frame buildings will survive the earthquake. Otherwise, if we design with this analytical period, we don't use that period, then all the buildings are having 60% probability of failure, very large probability of failure. Okay, if you use bare frame period to design infilled frame.
So that is conservative.
That is safe, I should say. It's not really very conservative. People think that it is very conservative, it is unnecessary, why we are designing for so much force, why we are putting so much money, but it's not the case. We have to look the whole thing in totality.
So next question from Sudeep is for a selection of time history for NLTHA, do we require to perform site-specific response analysis? So selection
you may
of
or may not
history.
do. You may or may not do. You can perform. You can select the time histories based on uniform hazard spectrum given in the code, or you can perform a site-specific spectrum, UHS again, or you may perform. You may make a CMS, conditional mean spectrum, or CS, conditional spectrum. Any of these spectra can be used. Of course, as we move from uniform hazard spectrum or from code design spectrum to site-specific uniform hazard spectrum to CMS to CS, the accuracy goes on increasing. But depending on what is available to you, any of these you can use.
So Sarad Adhikari is asking, to conduct nonlinear time history analysis, do we have to perform seismo matching with respect to our design spectrum? If yes, why we cannot design by same earthquake without matching?
First of all, why matching is done? Matching is done because the response spectrum, as I have shown you, response spectrum of actual ground motion and what is given in the code is very different. Even when you consider several ground motions, I have shown that comparison, even when you consider several ground motions and you take mean of that, even then the response spectrum is very different. So that you cannot use the ground motion as it is, you cannot use. So one way of doing that is this spectral matching. So in spectral matching, we try to change the characteristics, the frequency content of the time history in such a way that the response spectrum matches. But that is not considered to be a good way of doing that. What is done, that we should choose the ground motions as close to our response spectrum as possible. We should not take any randomly selected ground motions. The ground motions themselves should be selected, which are close to my target response spectrum. So that is the new one.
So then Roshan Shrestha asks, why there is 80% effective stiffness in uncracked wall sections? Shouldn't it be 100% for uncracked wall section?
Okay.
Why
Okay.
reduce?
So for that, we have to look at the definition of cracked and uncracked. So cracked and uncracked under which load? So cracked and uncracked is under the reduced load. So even if it is uncracked under the reduced load, the whole section remains in compression. Even during earthquake, because earthquake force is going to be much larger. So even that wall is going to crack during earthquake. So when we are saying cracked or uncracked, we do not mean cracked or uncracked during the actual earthquake. Cracked and uncracked under the reduced earthquake force. That's why we have to consider a reduction even in uncracked shear wall.
So he's also asking which load combination actually to be considered in foundation design, especially raft. Like load combination, is it only D plus L or other also?
See, in foundation design, there are two designs. One is the structural design of the foundation, and another is the geotechnical design of the foundation. Structural design is based on limit state method, RCC design. For RCC design, you will be using the same load combinations which you are using for column or beam. Same load combinations will be applicable. Geotechnical design may be based on working stress, whereas some codes may not be. Indian and Nepalese code are still not doing limit state method. Those are still based on working stress method. In working stress method, you have to use the working loads, which are coming from the deterministic median value. I mean, one difficulty which you people are going to have is how to design, how to check the stability of the foundation, geotechnical design of the foundations using NBC105, because it does not deal with those load combinations which are to be used with the working stress method. So those load combinations need to be provided. That is roughly 1 over 1.5 times that. So if you reduce the earthquake load by 1.5 till the code committee gives you something, I can suggest you one thing, that you use 1 over 1.5 earthquake load for geotechnical design of foundations. That is same. If you that ratio of 1.5 is everywhere. In Indian code, it is there. For working stress method, the load factor of earthquake is 1. In limit state, it is 1.5. In ACI, if you look at ACI 318, working stress method is 0.67, earthquake load is 1. 0.67? Yes, 0.67. Yes. So that is also 1 over 1.5. 0.67 or 0.7.
So we have less time. Shall we take more questions, sir? There are more questions.
Okay.
It means, Sudeep has again asked, it means we have to take response spectrum demand from NBC rather than SP114 for bridge design. We are interested in non-linear analysis of code exceeding building.
Of course. You can borrow the procedures, the methods from any country, but you cannot borrow hazard. Hazard has to be for your country. So hazard part cannot be borrowed from India or from anywhere. So if you have to design the bridges now, you have to follow the hazard from NBC 105. You should do that.
Yes, actually, in Nepal, infrastructure of building and bridges are checked by different departments. So Department of Road has not yet adopted that NBC 105 code. So still we are doing with IS1893 or SP102 we are doing. So,
there won't be much difference later because Indian code hazard is also being revised, and in the Himalayan region that will be upgraded. It will be increased. So it will come out to be more or less at par with what we are getting in Nepal. But again, it will not give. It is not going to give you any contour or any zone within the Nepal. That's the problem. That you have to interpret. So if you take it as the highest zone, seismic zone 5 currently, then it is okay. But if you try to take the adjacent zone, then it may not match, because you have seen the seismicity towards China is also reducing, seismicity towards India is also reducing. It is maximum within the Nepal itself. So if somebody borrows it from China, then also it will be wrong. If somebody borrows it from India, that will also be wrong. So you have to interpret it higher than both.
So next, DRP. DRP asks, IS1893 explains the different height and base shear to be considered for building with basement. Okay. So if there is a basement with complete retaining concrete shear wall, can we ignore seismic weight of the basement part? Could you please clarify the separation of the, so that is a separate question. So one is, can we ignore the seismic weight of basements?
Yeah, but we are not only ignoring the seismic weight, we are reducing the height also. The height will be considered above that itself. So the period is going to reduce. So the force is going to increase. So you are right. You have to reduce the height, and at the same time, for calculation of the base shear, you can ignore the weight of the basement. But for design of the basement walls, you have to consider the mass of the basement in the missing mass correction. Okay, so actually what is happening? The basement is vibrating along with the soil. It is like that rigid block which I was talking. So it's not that on rigid block the force is not acting. On the rigid block also force is acting. How much is that? That is equal to Z. So the whatever is the mass of the basement, that will be multiplied by Z. And the building above, which is tower, which is vibrating, that will be vibrating with its period. So their CHT will be calculated based on that period, and that will be added. This multiplying by Z, this is also called missing mass correction, because when you will do modal analysis, you will never be able to get 90% mass participation because basement doesn't vibrate along with it. So that is known as missing mass. And what we do, missing mass, we multiply by Z, as if its period of vibration is 0. It is not having, because we are having longest period in the first mode, and then period goes on reducing. And if period is 0, we will not get that participation in our mass. So that's why we call it missing mass. And that missing mass, we can missing mass correction we can apply by simply multiplying that mass by Z. So that is to be done.
So DRP adds another question. Could you please clarify the separation of building as NBC105 explains a sum of displacement which is resulting higher separation gap? Okay.
Right. Maybe, I mean, this is a suggestion. Code is what code has said, what your interpretation of code is, that is correct. But what is seen is that if the two floors are at the same level, that means it is an expansion gap between the two buildings which are having floors at the same level. There, the damage will be less, because when floor is hitting the floor, the damage will be less. If the floor is hitting the column, the damage will be more. So if the floors are at different height, then there is no choice. You have to add the displacement from both the sides. What the Indian code does, if floor is hitting the floor, then you can take half of that. So maybe if your authority agrees to that, in case of buildings having floors at the same level, you can reduce the gap to half. Because I agree, in case of a tall building, this gap comes out to be really huge. Expansion gap becomes a real gap.
So then Utkarsh Ritual has asked another question. Why the value of spectral shape factor CST is taken as 2.5 for lower time period inequality? I think he has answered this question or not.
Yeah, I raised this question that I will answer, but then I forgot why it is done. Okay, it's like this, that when we are considering modal analysis, we are considering several periods, and higher periods can come below 0.1. Okay, when we are considering equivalent static method, we are considering only one mode, fundamental mode, and fundamental mode period of even one-story building will be 0.1 second. It cannot come out to be less than that. But suppose due to the empirical formula, which is conservative, the period comes out to be less than 0.1 second, then what you will do? You will be underestimating the forces. So there is an error. Due to error, you are underestimating. So to take care of that error, the code has flattened it right up to 0, so that you do not, your period does not fall into that gap which is created between 0 and 0.1 while you are performing equivalent static method. That's why it is taken flat to 0.
Okay, so there is one question from Tim Lal Das. A class video recording is available. So then DRP on So Anusa Baral asked, during the stiffness modifier, the overall stiffness is reduced, thus it reduces the beam moment and transfers to column. So what will be in reinforcement? So what is the
No, no,
effect of
it is not
stiffness
reducing.
modifier? Yeah, okay.
It is not reducing. Why it is not reducing? Because we are scaling up the forces. The forces we are scaling with the empirical period, BB bar, which we have calculated. So because the forces are, you will be calculating, the model will be giving you the lower forces, but then you are applying a scale factor. So you are bringing it to the same level at which uncracked section will give. Then why we are using cracking? If we have to scale the forces, in any case, finally, the scaling, this cracking modification is done for calculation of displacement, because the displacement is going to increase. If you are using uncracked section, you are underestimating the drift. So that the drift is not underestimated, that's why cracked section is used, and forces are again calibrated back to the uncracked value.
Okay. So then last two questions now. Taken Pandis as stiffness modifier used for serviceability check only, or use the reduced value for design of member also?
As I said, on design of member, it will not have any effect because
Yeah.
the forces in any case will be scaled. So don't think that if you are using the stiffness modifier, the forces are going to reduce. Forces will not reduce. Forces will be same. Displacement will increase.
So then Utkarsh Vetwal asks, why IS1893 code recommends to use vertical earthquake for every structure in zone 4 and 5, but NBC only recommends for vertical earthquake of beam span greater than 20 or cantilever greater than 5. So why there is difference?
As I said, that vertical component will be acting on all the structures. Some of the structures it will be critical, some of the structures it will not be critical. Earlier days, when analysis was to be done manually, then the codes used to specify that here it is must to consider, here you may or may not consider. Now it is to be done by computer. So that's why I am suggesting that consider all the components of earthquake in all the cases. Wherever it will not be significant, it will not affect your reinforcement. Wherever it will be significant, it should affect your reinforcement. So actually the vertical component of earthquake will act on all the structures of all the span, shorter or bigger. Long span structures, the effect will be more. On the short span structures, the effect will be less. That's it.
Yes, so last question is from DRP. Is 1904 1896? So I think that is Foundation Design Code. Clause 15.1.7. If earthquake or / wind load exceeds 25% of gravity load, foundation design needs to be designed for DL plus LL plus EQ. Under what case? Example, EQ greater than 0.25 into GL.
I'm sorry, I have not understood that clause. I have not seen that. So please send me that email, or I will get it from here. And just write an email to me. I will answer. I have to go through that code before answering this question.
So we have come to the end of our questions. So if any participants want to give feedback on this forum, they are free to raise hand and speak for a while. Maybe 1 minute we can have for 2-3 participants. So I see no raise hands. So I think all of them are satisfied and still thinking what professor has given so many new ideas. So they are still churning those ideas in their brain. So I think I'd like to stop this webinar for today at this point. So for the closing remarks, I'd like to be extremely thankful. Okay, so there are some thankful comments in the message section. So for the closing remarks, I think Yogesh Bhattrai sir is there. So could you please propose the word of thanks, and then we'll meet again on next Saturday.
Thank you, everyone, and especially thank you to our Professor Dr. Yogendra Singh for conducting this session. And NBC, there was a recent revision that has been really well captured by Dr. Yogendra Singh, and he has been commenting about the displacement relation that some omega term is also missing. And we'll be very happy, sir, if we clear that doubt and the next amendment shows that correction. And I hope everybody have learned something even we too have learned something, and we always get to learn something from sir whenever, whatever stage we are in of our life. And thank you everyone. Thank you.
Hello, sir.
Okay,
Thank
so
you.
if it is
Hello.
over from your side, I also want to thank the organizers who has made this possible, especially the persistence from Yogesh side, that I was a bit hectic schedule I was having during these days, so I was a bit reluctant, but he persuaded me. And thank you all who are coming to hear me, okay, who were here and asked questions, interacted. And that's what a teacher looks for, that there should be always audience to listen to him. So thank you very much. And we will meet next Saturday. And there I will talk about the background of ductile detailing. Okay, first, that what is the basis of those clauses which are there in our code. And then we will talk about the clauses of the code. Thank you.
Thank you, sir. Thank you, sir. Excuse me, sir. Sir, I have a question, sir.
Please.
Sir, should you consider earthquake load in designing a raft foundation, or we should just consider load combination tail load or live load only?
No, we should consider earthquake. All the load combinations should be considered. So
while
whatever
designing
load combinations we are using for beam and column, the same load combinations are to be used for raft design.
Yeah, just one friend mentioned that IS1893 foundation code. It is included that if load is earthquake load is 25% less or something like that, we can design foundation without considering the earthquake load. It is mentioned that in the code,
First of all,
somewhat like that.
That code is about geotechnical design. So in geotechnical design, we are having working stress method. In working stress method, 33% increase in the working stress is taken, permissible stress is taken when we are considering earthquake. So if earthquake force is less than 25%, then it will be covered by that 33% increase. That's why that code says. But that is regarding the geotechnical design. Do not confuse it with structural design. Structural design of foundation is covered by IS456. Okay. And IS456 does not say anything like that. So there you have to use the load combinations of IS1893. All the combinations of IS1893 are to be used in all the building foundations.
Yes, so thank you for your question and response, Professor. So more questions later can be asked in the next seminar, or we can also email them to Professor if anybody of you sends.
Yes, anybody wants to ask anything, please write an email. I will try to answer. Sometimes it gets delayed because of the hectic schedule, but I will try my best to answer.
Yes. So with this, I would like to also mention that the video recording of this webinar will be available to the participants who have registered. And today is World Non-Violence Day also. So I think by discussing about earthquake, which is the most violent force for Nepal, we have justified the day and celebrated it well. So I'd like to thank all the participants and have a good evening and good night. Thank you. So
Thank you. Thank you.
Webinar closes here. Thank you.
Thank you, sir. Good night.